If you have ever stood beneath a truly dark night sky, far from the lights of civilization, and looked up at the Milky Way, you likely felt a very strange sensation. It is a feeling that goes far beyond the word spectacular. It is a tremor of near instinctive awe, because in that moment, you suddenly realize that pale band of light spanning the night sky is not a cloud. It is not a mist. It is hundreds of billions of stars. In ancient times, many civilizations imagined the Milky Way as a literal river flowing across the heavens. The ancient Greeks believed it was the milk of the goddess Hera, spilled across the sky. In ancient China, it was called the Silver River, a vast celestial current forever separating the star-crossed lovers, the cowherd and the weaver girl. And in Norse mythology, the Milky Way was sometimes seen as the path of souls, journeying to the far side of the universe. For a very long time, humanity had no idea what it truly was, because it seemed too vast, too immense to be a mere object. It felt like a part of the fabric of heaven itself, until much later, with the invention of the telescope, humanity slowly began to understand that faint white ribbon of starlight arching over the night sky is actually the interior of a colossal galaxy, and we are standing inside it. Today, we call this galaxy the Milky Way, a massive stellar structure spanning roughly 100,000 light-years in diameter, holding within its frame 100 billion to 400 billion stars, and our Sun is just one extraordinarily ordinary star among them. But the question that is truly fascinating is this: why does the Milky Way take this specific shape? Why does it appear in our night sky as a narrow band of light, rather than a uniform blanket covering the entire heavens? The answer is actually beautiful in its simplicity, because the Milky Way itself is shaped like a massive, slowly spinning cosmic record, or to be more precise, like a flattened storm of stars. And we happen to live right along the inner edge of this record. Imagine for a moment that you are a tiny ant living inside a flat pizza. If you look straight up or down toward the surface, you see only a thin layer. But if you look out along the flat plane of the pizza, your vision travels through a vast expanse of material. And so you would see a much brighter, much denser band. The Milky Way is exactly the same. When we look toward the galactic plane, our line of sight cuts through hundreds of millions of stars. And that is how that hazy silver-white river is formed across our night sky. In a way, humanity has never truly seen the Milky Way galaxy, because we are inside it. Just as a single grain of dust cannot perceive the entirety of the desert, those overhead views of the Milky Way you see online today, those spectacular images of grand spiral arms, glowing centers, and gentle rotation, most of them are merely scientific reconstructions and models, because we cannot fly outside the Milky Way to take its picture, at least not yet. But in recent years, as the James Webb Space Telescope began its work, humanity has seen, with unprecedented clarity, extremely distant, extremely ancient galaxies. Some of these galaxies formed shortly after the birth of the universe itself, which means when the light from those stars began its journey toward us, the Earth did not even exist. The solar system had not yet formed, and the Milky Way itself may have been nothing more than a young, primitive structure, because most of us have carried a misconception about our galaxy since childhood. Many people subconsciously assume the Milky Way is static, that the stars are just hanging there, like light bulbs in the night sky. But in reality, the Milky Way is a colossal dynamic system where almost everything is in motion. The Earth is orbiting the Sun at a speed of roughly 30 kilometers per second, and the Sun itself is traveling around the center of the Milky Way at a staggering pace, cruising at 220 kilometers per second, which means right now, as you lie in bed watching this video, our entire solar system is hurtling through the galaxy at a speed that completely defies human intuition. Yet even at this velocity, for the Sun to complete just one single orbit around the Milky Way, it still takes roughly 230 million years. This scale of time is almost impossible for our minds to grasp. Consider this. The last time our solar system was in this exact galactic position, there were no humans on Earth. In fact, dinosaurs were only just beginning to appear. In other words, from the dawn of the dinosaurs to this very day, the solar system has not even completed one full journey around the Milky Way. And what is even more extraordinary is that the Milky Way itself is moving, drifting slowly through the universe, alongside its cosmic neighbors, the most famous of which is the Andromeda Galaxy. If you live in the northern hemisphere and look up on a truly dark night, you can even see it with the naked eye, a faint fuzzy patch of light. But that little smudge of light is actually another entire galaxy, holding within it over 1 trillion stars. And it is moving toward us. In about 4.5 billion years, the Milky Way and the Andromeda Galaxy will collide. However, the word collision can easily be misunderstood because galaxies do not crash into each other like cars. The distances between stars are vast, so the probability of a direct stellar impact is actually incredibly low. More precisely, it will be a process lasting billions of years. A gravitational fusion. The two colossal galaxies will gradually pass through one another. Spiral arms will be torn apart. Stellar orbits will alter. New regions of star formation will ignite. And the entire structure of the night sky will change forever. In the end, the Milky Way will likely lose the beautiful spiral arms it possesses today, slowly transforming into a larger, more chaotic, elliptical galaxy. In fact, this is the ultimate destiny of many massive galaxies across the universe. And at the heart of all this is rotation, because rotation is precisely what keeps the Milky Way stable. What would happen if the Milky Way did not spin at all? The answer is, it would collapse, because stars are not static, hovering in place. The reason they do not all plunge into the galactic center is because they are in motion. It is a bit like a mace being spun through the air. The tension on the rope is gravity, while the circular motion of the weight prevents it from falling inward. The Milky Way functions the exact same way. The immense gravitational pull at the center of the galaxy is constantly drawing stars inward, while the high-speed orbital motion of the stars maintains the balance of the entire system. And so, a massive cosmic whirlpool is born. But here lies an even deeper mystery. Why do the stars on the outer edges of the Milky Way spin so fast? By all accounts, the further a star is from the center, the slower it should rotate. Just like our solar system, Mercury orbits the fastest, Neptune the slowest. But that is not what happens in the Milky Way. Scientists later discovered the speed of the stars on the galactic fringe is impossibly fast. Based on the calculations of visible matter, those stars should have flown off into deep space long ago. But they have not. They remain tightly bound to the galaxy, as if something invisible is providing extra gravity. And so, one of the most enigmatic concepts in modern astronomy emerged: dark matter. Even today, humanity still does not know what dark matter truly is. We cannot see it. We cannot detect it directly. It emits no light, reflects no light, and rarely interacts with ordinary matter. Yet stranger still, the entire universe appears to be filled with it. Scientists theorize that the true form of the Milky Way is not just the glowing whirlpool we see. Beyond the stars, the nebulae, and the spiral arms, it is enveloped by a massive, invisible dark matter halo, like an unseen ocean, cradling the entire galaxy within its depths. And the stars within the Milky Way are merely lights drifting on the surface of this invisible sea of gravity. Without dark matter, the stable rotation the Milky Way exhibits today could likely never be sustained. It is a profound realization. Since childhood, we look up at the night sky, believing the universe is made of the things that shine: the stars, the planets, the nebulae, the Milky Way. Yet modern astronomy tells us everything we can see may account for only a tiny fraction of the cosmos. The force that truly sustains the rotation of the galaxy may be the very thing we can never look upon. In a sense, the Milky Way is like a ghostly structure, where we can only glimpse the light on the surface. And what is more fascinating is that the way the Milky Way spins is entirely different from what most people imagine. When most people see an animation of the Milky Way for the first time, they instinctively assume it spins just like a slowly rotating vinyl record, where every region turns together at the exact same pace. But reality tells a different story. The Milky Way does not exhibit rigid rotation. It functions more like a colossal system of cosmic ocean currents, where different regions rotate at entirely different speeds. The areas closer to the galactic center revolve much faster, while the outer regions move at a comparatively slower pace. This phenomenon is known as differential rotation. You can visualize it like a cup of coffee being stirred, where the speed of the central swirl and the liquid at the edge are not the same. And this introduces another puzzle. If different regions of the Milky Way move at varying speeds, then why haven't those beautiful spiral arms been stretched thinner and thinner until they are completely wound up and distorted? The answer is actually profoundly elegant. Because the spiral arms of the galaxy are not fixed physical objects. Many people believe that galactic arms are permanent, massive ribbons of specific stars. They are not. They are closer to a cosmic traffic jam. This is a classic analogy in modern astronomy. Imagine a section of a highway where traffic suddenly slows down. Cars from behind begin to bunch up, creating a localized bottleneck. But the traffic jam itself is not made of a permanent set of vehicles. Cars are constantly entering the jam and constantly leaving it. The spiral arms of the Milky Way are exactly the same. They are actually a manifestation of density waves. Stars are continuously entering a spiral arm, linger there briefly, and then move on out the other side. What truly accumulates within these arms are primarily gas, dust, and newly born young stars. Because within these zones, matter is compressed and more tightly packed, triggering the birth of new stars. And that is why the spiral arms appear so exceptionally bright to our eyes. As for our solar system, at this very moment, we reside near a minor spiral arm of the Milky Way, known as the Orion Arm. It is not part of the primary, central structures of the galaxy, but sits further out, closer to the edge. In a way, this is a stroke of cosmic fortune, because the center of the Milky Way is far more hazardous than people tend to imagine. Stellar density there is incredibly high. Supernova explosions are more frequent. The radiation environment is highly complex. And then, there is a true monster, the supermassive black hole at the center of the Milky Way. Its name is Sagittarius A star. This is a colossal black hole with a mass roughly 4 million times that of our Sun. Yet, remarkably, it appears entirely serene. Many people assume that the central black hole must be frantically devouring everything around it like a science fiction movie, unleashing blinding torrents of energy. But that is not the case, at least not right now. At present, Sagittarius A star is in a relatively dormant state. It is not actively consuming massive amounts of surrounding matter, which is why it does not possess a spectacularly bright accretion disk. Even so, it still dominates the gravitational architecture of the central galactic region. More importantly, there is a common misconception that the Milky Way rotates because the central black hole is dragging the entire galaxy around with it. That is simply not true. The black hole is undeniably important, but its mass, relative to the entirety of the Milky Way, represents only a tiny fraction of the whole. What truly dictates the rotation of the galaxy is the distribution of total mass across the entire system, including the stars, the gas, the dark matter, and the overarching gravitational structure. However, the black hole itself does indeed rotate. In fact, almost all black holes in the universe spin, and some of them rotate at unimaginable speeds, approaching the absolute limits of physics. Because black holes typically originate from the collapse of massive stars, and those stars were already spinning to begin with. According to the conservation of angular momentum, when a massive celestial body continues to shrink, its rotation speed becomes faster and faster, just like a figure skater pulling in their arms, spurring an immediate acceleration. When a star collapses into a black hole, this effect becomes extraordinarily exaggerated. And so, one of the most extreme rotating objects in the universe is born. The space-time surrounding certain black holes can even be dragged along by its rotation. This is called frame dragging. Simply put, the black hole is not merely spinning through space. It is actively dragging the fabric of surrounding space-time along with it. This is a genuine prediction of Einstein's general theory of relativity, and it has since been verified by observation. So, in a sense, at the very center of the Milky Way, there exists a colossal abyss, slowly twisting the fabric of time and space. But here comes the truly fascinating question. If one day the Milky Way stopped spinning, what would happen to the central black hole? The answer is actually quite complex, because the galaxy ceasing to spin does not mean the black hole would immediately stop rotating. The black hole could continue its own internal rotation, persisting for billions of years. What would truly change is the underlying order of the entire galactic system. Stellar orbits would begin to drift into chaos. The spiral arms would gradually vanish, and the once stable galactic disk structure would slowly dissolve. And this is not pure fantasy within our universe, because many galaxies have actually experienced a similar process. Most notably, through galactic collisions, the galaxies in our universe are far less stable than people tend to imagine. They draw close to one another, tear at each other, devour each other, and even merge completely. If you look at photographs taken by deep space telescopes, you will find that some galaxies possess incredibly bizarre shapes, like elongated droplets, like twisted smoke, like glowing clouds with long, trailing tendrils. These are almost always galaxies in the midst of a collision. One of the most famous examples of this is known as the antennae galaxies. Two galaxies are currently passing through one another. Immense gravitational tides are pulling stars and gas into vast ribbons of light. The entire image looks like two melting whirlpools in the cosmos. And during this collision process, the originally stable rotational structure of the galaxies is gradually disrupted. Massive numbers of stellar orbits begin to randomize, The spiral arms are torn to shreds. In the end, two beautiful spiral galaxies may merge into a single, massive, slow, and nearly irregular elliptical galaxy. In fact, many astronomers believe that the large elliptical galaxies in our universe are likely the result of countless galactic mergers. They do not possess clear spiral arms like the Milky Way, nor do they have a distinct disk structure. The motion of the stars inside them is far more random. The overall rotation is weaker, appearing more like a colossal cloud of stars. And those non-rotating galaxies, recently discovered by the Webb telescope, in a way, may be forcing us to rethink how the earliest galaxies in the universe were actually formed. Because for a long time, scientists always took for granted that after a galaxy forms, it should naturally develop a rotational structure. But now it appears there may have been an entirely different evolutionary path in the early universe. Some galaxies, perhaps from the very beginning, never formed a stable rotation. They are closer to a slowly gathering system of stars, rather than a grand whirlpool. This realization is profoundly important because it means the current state of the Milky Way today might not be the universe's only normal form, and perhaps rotation itself is merely a passing phase in cosmic history. And if you continue to stretch the horizon of time, you will see that the entire universe, in fact, is slowly growing old. The young universe was completely different from the one we see today. In those early days, galactic collisions were much more frequent. Stars were being manufactured at a much faster pace. The cosmos was flooded with hot blue young stars. Colossal gas clouds were continuously collapsing, and supernovas erupted one after another. The entire universe was like an ocean still engulfed in flames. But today, the cosmos has grown far quieter. The rate of star formation is steadily declining. More and more galaxies are entering an aging phase. And within certain stellar systems, the birth of new stars has nearly ground to a halt. These systems are sometimes referred to as dead galaxies. Of course, dead in this context does not mean the stars have all burned out. Rather, it means they have lost the capacity to produce new ones. Because the most critical raw material for star formation, cold gas, has gradually been exhausted. And so, the entire galaxy slowly dims, turns red, and grows cold. In the end, nothing remains but a vast population of elderly stars, drifting slowly in orbit. In a way, the Milky Way will eventually undergo a similar process, billions of years from now. The blue young stars within the Milky Way will grow increasingly scarce. The night sky will gradually shift toward a deeper crimson. Star-forming regions will slowly go dark, and those nebulae, which look like cosmic fireworks today, will gradually dissipate. The entire Milky Way will settle into a long, slow twilight, and the rotation itself will actually begin to diminish during this process, because every galactic collision, every gravitational disturbance, will disrupt the once orderly orbital structure. Ultimately, a young spiral galaxy with sharply defined arms may slowly transform into a massive, blurry, and nearly static elliptical galaxy. Yet, in a sense, stopping rotation does not necessarily mean a catastrophe. It is closer to an aging process on a cosmic scale. Just like a turbulent river in its youth, eventually settling into a calm lake. However, for any civilization living within the Milky Way, this transition could still prove to be highly dangerous, because once the Milky Way loses its stable rotation, many structures that were once perfectly balanced will begin to shift. The first thing to change will be the orbits of the stars. Right now, Our solar system is traveling along a relatively stable path, orbiting the center of the Milky Way. But if the overall structure of the galaxy falls into chaos, the orbit of the solar system could gradually drift. We might be hurled toward the outer fringes of the galaxy, or we could slowly draw closer to the galactic center. And the latter would be a profoundly hazardous outcome, because the closer you get to the galactic center, the more unstable the cosmic environment becomes. That region holds a much higher density of stars, more supernovas, intenser radiation, and far more complex gravitational disruptions. If the solar system were to enter such a zone, life on Earth could face long-term threats. For example, a nearby supernova explosion. When a massive star dies, it unleashes an astonishing amount of energy. For a brief period, its brightness can outshine an entire galaxy. And if such an explosion occurs too close to Earth, the resulting high-energy radiation could destroy the ozone layer, alter the climate, and fundamentally disrupt biological evolution. Scientists believe that certain mass extinction events in Earth's history may have been linked to nearby supernovas. And beyond the stars themselves, a shifting galactic structure could also disturb another massive region, long hidden on the outer edges of the solar system, the Oort cloud. This is an incredibly distant cloud of icy bodies, enveloping the entire solar system. Many long-period comets originate from there. Normally, the objects within the Oort cloud drift quietly in the darkness of space. But if the galactic gravitational environment changes, or a neighboring star passes too close, these frozen bodies, sleeping for billions of years, could be destabilized. A massive influx of comets would suddenly plunge into the inner solar system. You can imagine a once quiet night sky suddenly filled with frequent, colossal comets, some of which might even strike the planets. In reality, the history of Earth has always unfolded amidst these cosmic perils. It is only because human civilization has existed for such a brief moment, so brief that we mistake the universe for a stable place. But the universe has never been stable. Stars explode, galaxies collide, black holes devour stars, gravity tears orbits apart. The entire Milky Way has always been in a state of slow, constant change. It is just that. The timescales of these shifts far exceed the span of a human life, and so they appear to us as eternal and unchanging. But if you speed up time, compressing billions of years into a few minutes, the Milky Way would look like a literal storm. Spiral arms shifting continuously, stellar orbits drifting back and forth, dwarf galaxies being consumed, gas clouds colliding, new stars being born, old stars fading away. The entire galaxy has never been a static backdrop, but a living system. In fact, humanity has discovered today that the Milky Way is still actively devouring other smaller galaxies, the most famous of which is the Sagittarius Dwarf Elliptical Galaxy. This is a small companion galaxy currently being torn apart by the Milky Way. The galaxy's intense gravity is continuously stretching it, shredding it. In the end, it will completely merge with the Milky Way, and the stars that once belonged to it will be scattered into the galaxy, becoming part of new stellar streams. In a sense, the reason the Milky Way is so colossal today is precisely because it has devoured many other galaxies throughout its past. Galaxies in the universe rarely ever grow up alone. They are much like civilizations that constantly merge, consolidate, and consume one another. And even more extreme events can take place between the black holes at the centers of these galaxies. When two galaxies merge, the supermassive black holes at their cores will also gradually draw closer together until finally they collide. This is one of the most terrifying events in the cosmos. two supermassive black holes orbiting one another, releasing immense gravitational waves, causing the very fabric of space-time to ripple and shake. Ultimately, they merge into an even larger black hole. But the story does not end there, because in certain cases, the gravitational waves released by the merging black holes are not completely symmetrical. As a result, the newly formed black hole is kicked away by a kind of cosmic recoil, hurled directly out of the galactic center. This phenomenon is known as gravitational wave recoil, which means a galaxy can actually lose its own central black hole. This is a profound revelation because many people instinctively assume the central black hole of the Milky Way is anchored there forever. But in reality, even black holes themselves can go wandering through the universe after a cosmic collision. Scientists even theorize that the universe may be filled with rogue black holes, drifting alone through interstellar space, emitting no light, nearly impossible to observe. Only when they accidentally pass near a star and generate a gravitational lensing effect does humanity have any chance of discovering them. Yet compared to black holes, there is something even more profoundly isolated: rogue stars. Some stars are flung out at high velocities during galactic collisions. They break free from the Milky Way, entering the dark voids of intergalactic space, no longer belonging to any galaxy at all. Out there are no spiral arms, no dense populations of stars, no brilliant night sky, only the genuine abyss of deep space. If a civilization were to live in such a rogue star system, their night sky would no longer feature a Milky Way. Above them, only a handful of distant, isolated pinpricks of light. The entire universe would appear utterly empty. And all of this is simply because the order of motion in the universe was altered. In fact, when you begin to truly study galaxies, you slowly discover a very strange truth. Stability in the cosmos is often only temporary. The reason humanity perceives the Milky Way as eternal is merely because our lifespans are so incredibly brief, too brief to ever witness the shifts of the galaxy firsthand. If a human being could live for billions of years, the night sky before their eyes would be entirely different. Constellations would warp, stars would shift position, the spiral arms of the Milky Way would slowly drift, and the Andromeda galaxy would grow larger and larger. Ultimately, the structure of the night sky itself would change completely. In reality, even on a scale of just tens of thousands of years, the sky already shows noticeable differences. The Big Dipper, so familiar to us today, will morph into an entirely different shape in the distant future, because the stars that compose it were never truly bound together. They just happen to look close from Earth's perspective at this point in time, and the shifts on a galactic scale are even more staggering. For instance, the Milky Way does not exist in isolation. It belongs to a much larger structure, the local group, which includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of dwarf galaxies. And the entire local group is itself moving toward an even grander structure, the Virgo supercluster. Even more mind-boggling, the entire supercluster is traveling toward a region known as the Great Attractor. In that direction lies some immense concentration of mass, whose gravity is pulling countless galaxies toward it. But the catch is, that region is obscured by the dusty plain of the Milky Way, preventing humanity from seeing it clearly for a very long time. So, to this day, regarding what the Great Attractor truly is, many unknowns remain. It is a fascinating sensation. Humanity is capable of observing the universe over 13 billion light-years away, Yet we still cannot completely see the very thing that is pulling us. And what is even more incredible is that even though galaxies are pulling on each other, the universe as a whole is continuously expanding, and the rate of expansion is accelerating. Scientists later discovered that distant galaxies are moving away from us, not because they are actively flying through space, but because space itself is expanding. This concept is entirely counterintuitive, because the motion we understand since childhood is typically objects moving times through time's space. But cosmic expansion is more like space itself being stretched. You can imagine drawing dots on the surface of a balloon. As the balloon inflates, the distance between every dot grows larger, and the galaxies are like those dots. This means the entire universe, from the moment of its birth, has always been in a state of dynamic change. Nothing is truly static. So in a way, stopping rotation itself is a state that violates the fundamental instinct of the cosmos, because motion is practically written into the foundational rules of the universe. The motion of planets, the motion of stars, the motion of galaxies, the motion of electrons, even time itself seems to signify change. And that is why a galaxy that truly no longer rotates appears so uniquely bizarre. It looks like a region of absolute stillness frozen in the cosmos. And those ancient galaxies discovered by the Webb telescope may be telling us that the early universe once harbored entirely different evolutionary paths. Perhaps the first galaxies were not as orderly as the ones we see today. Perhaps a grand whirlpool structure like the Milky Way is actually the refined product of long-term cosmic evolution. And maybe the Milky Way we look upon today is merely a brief, passing phase in cosmic history. In another few billion years, it will transform into something else entirely. In fact, the Milky Way is already far from its original form. By analyzing the orbits of stars, scientists have discovered that the Milky Way has devoured many small galaxies in the past. Some stars are not actually native residents of the Milky Way. They originated in older, smaller galaxies and were later absorbed by our own. These stars still retain distinct orbital paths today, like cosmic fossils. By analyzing them, astronomers can reconstruct the story of what happened to the Milky Way billions of years ago. It is a bit like archaeology, except the subjects of this archaeology are not the ruins of ancient civilizations, but rather the entirety of the galaxy itself. And the deeper scientists delve into their research, the more they discover that the Milky Way is far more chaotic than it appears. For instance, the galactic disk is not perfectly flat. It possesses a slight warp. Certain regions ripple up and down, like fabric drifting in the wind. Scientists believe this disruption may be caused by the passing of neighboring dwarf galaxies, or an uneven distribution of dark matter. In other words, even today, the Milky Way is not a truly stable, perfectly symmetrical structure. It is constantly being influenced by the surrounding universe. And out on the fringes of the galaxy lies an even more mysterious region, the galactic halo. The matter there is incredibly sparse, with very few stars to be found. Yet it is heavily populated by globular clusters. These globular clusters are ancient, many with ages approaching that of the universe itself. They are like relics left behind from the earliest days of the Milky Way. If the Milky Way were a city, then these globular clusters would be like the ancient ruins out on the edge of town. And stranger still, the orbital paths of some of these globular clusters do not even align with the overall rotation of the galaxy. They are like eccentric ancient residents, silently orbiting along the galactic fringe. And all of this points to one single truth. The Milky Way is not a simple structure. It is more like the accumulated result of countless histories. Every collision, every consumption, every gravitational disturbance leaves a scar within the galaxy. Therefore, if the Milky Way stops rotating in the future, it does not necessarily mean an abrupt, sudden halt. It is far more likely that after countless collisions and chaotic disruptions, the originally orderly rotational structure will slowly dissolve away, and in that distant future, the night sky will change completely. The night sky humanity looks upon today is actually a stroke of immense fortune. We are neither at the chaotic center of the galaxy, nor out on its desolate edge. We are situated in a relatively peaceful neighborhood. The stellar density around us is moderate. Supernova explosions are rare. Heavy elements are sufficiently abundant, and there is no overpowering radiation environment. Many scientists even believe this specific galactic location may itself be a vital precondition for the birth of life. Because if the solar system were too close to the galactic center, high-energy radiation could permanently disrupt biological evolution. And if it were too far out, heavy elements might be in short supply. After all, many of the elements that compose life, such as carbon, oxygen, and iron, all originate from the deaths of earlier stars. In a sense, humanity is actually the product of the galaxy's long-term stellar life cycle. The atoms inside our bodies right now once belonged to ancient stars. Those stars exploded billions of years ago, scattering their elements into the cosmos. Later, new stars formed, new planets emerged, and ultimately, life appeared on Earth. That is why Carl Sagan once said a very famous line, "We are all made of star stuff." This is not merely a poetic expression. It is a literal, physical fact. And if the Milky Way gradually stops spinning in the future, the rate of star formation will drop lower and lower. Fewer new stars will be born. Fewer new planets will form. The universe will slowly lose its capacity to create anything new. Ultimately, the entire galaxy may settle into an extraordinarily long period of silence. No more bright, blue, young stars. No more colossal nebulae. No more frequent stellar births. Nothing left but darkening red dwarfs, burning slowly, and then fading out one by one. Long ago, when humanity first realized the Milky Way was not just the background of the sky, many astronomers were profoundly shocked, because before that moment, it was widely believed that the Milky Way galaxy, perhaps asterisk, was times the entire universe. Until the early 20th century, with the advent of more powerful telescopes, scientists slowly discovered that many of those blurry little patches of light in the night sky were not nebulae at all, but rather entire, separate galaxies, each holding hundreds of billions of stars of their own. This discovery fundamentally altered humanity's understanding of its own place in existence, because it meant the Milky Way is nothing special. The universe is filled with countless other Milky Ways, and among these galaxies, some are uniquely bizarre. For instance, there is a type of galaxy that looks like a colossal ring floating in deep space. The center is almost entirely empty. The most famous example is called Hoag's object. It looks completely surreal, as if someone designed it intentionally. At its center is a golden yellow core, encircled by an almost perfect ring of blue stars on the outside. The entire structure is so exceptionally orderly that some have even speculated whether it could be an artificial construct built by a super civilization. Of course, there is currently no evidence whatsoever to support this idea. Scientists believe it is far more likely the aftermath of a unique galactic collision. But the catch is, to this very day, regarding how it formed, there is still no unified answer. The universe is filled with things like this. We can see them, yet we do not fully understand them. There are other galaxies that even possess two cores, which means within the central region of a single galaxy, there exist two supermassive black holes. Typically, this signifies that it once devoured another galaxy. After the two galaxies merged, their central black holes had not yet completely combined, thereby creating a double core. If you could stand inside a galaxy like that, the night sky would be completely different. Stellar orbits would be far more complex. The galactic structure would be warped, and dual jets of energy might erupt from the central core. And in some extreme scenarios, galactic collisions can trigger a firestorm of star birth. Vast quantities of gas collapse rapidly under intense gravitational pressure. New stars are manufactured at a frantic pace. The entire galaxy looks as though it has suddenly been set ablaze. These systems are known as starburst galaxies. The rate of star formation inside them can be dozens of times faster than that of the Milky Way. There are places in the universe forging stars with a speed that is almost violent. But at the same time, other galaxies have already fallen completely silent. This stark contrast is very much like a cosmic version of an ecological cycle. Some regions are young and furious, while other regions are ancient and still. And the Milky Way happens to sit precisely in an intermediate state. It is not as frantic as the youthful starburst galaxies, nor is it as dormant as the ancient elliptical ones. It is still slowly producing new stars, but at a rate far lower than during the youth of the cosmos. In a sense, the Milky Way is currently experiencing its midlife, and our Sun is a textbook example of a middle-aged star. It has been burning for roughly 4,600,000,000 years. In another 5 billion years or so, the Sun will begin to expand, transforming into a red giant. By that time, its volume will be breathtakingly immense. Mercury and Venus will likely be swallowed whole, and the Earth, even if it escapes being directly devoured, its surface will be completely scorched. The oceans will evaporate, the atmosphere will collapse, and the rocks will melt. Every trace of the civilizations that once existed will vanish. Yet strangely, even when that day arrives, the Milky Way itself will likely look almost exactly the same, because to the galaxy, the death of a single star is utterly ordinary. At every single moment, stars are being born within the Milky Way, and stars are fading out. The Sun will receive no special treatment. It will simply reach its end quietly, and then cast its own elements back into the cosmos, perhaps billions of years later. These very elements will take part in the formation of a new star, the formation of new planets, and even the formation of new life. This is actually an extraordinary, beautiful cycle within the universe. Stars do not merely shine. They are also responsible for manufacturing the cosmos. The universe, in the very beginning, was actually incredibly simple, containing only hydrogen, helium, and a tiny trace of lithium. Later, the first generation of stars emerged. Through nuclear fusion deep within their cores, they slowly manufactured heavier elements and then exploded upon their deaths. And so, carbon, oxygen, iron, silicon, and gold began to flood into the universe. If stars never died, there would be no rocky planets, there would be no oceans, there would be no life. So, in a way, life itself is the byproduct of the death of stars, and the rotation of the Milky Way is the crucial backdrop that sustains this entire cycle, because rotation influences the distribution of gas, the formation of stars, gravitational stability, and galactic structure. If the Milky Way were to completely lose its rotation, many regions would begin to collapse inward once more, while other regions might be flung out toward the distant fringes. The entire galaxy would become far more randomized. The galaxy's disk structure, which once resembled a vinyl record, would slowly thicken. More and more stellar orbits would no longer be confined to the galactic plane. The entire Milky Way would gradually transition from a spiral into a mere cluster. And this has actually already happened to many elliptical galaxies. Those massive elliptical galaxies we see today appear serene, blurry, and devoid of structure. But back in their youth, they very likely possessed beautiful spiral arms as well. It is just that after prolonged periods of collision and merger, their originally orderly rotation was gradually disrupted and scattered. In a sense, an elliptical galaxy is actually an elderly Milky Way, and for the future galaxy formed after the merger of the Milky Way and Andromeda, scientists have already given it a name: Milkomeda, the combination of the Milky Way and Andromeda. Billions of years from now, if some form of civilization still exists, the night sky they see above their heads will be entirely different. The brilliant band of the Milky Way that arches across our sky today will be gone, replaced, perhaps by a more uniform, hazy, and colossal cloud of stars. And Andromeda will no longer be that faint, distant smudge of light. It will dominate the entire sky. In fact, long before the Milky Way and Andromeda truly touch, the Andromeda galaxy in Earth's future night sky will grow larger and larger. Billions of years from now, it may look like a monstrous glowing whirlpool hanging in the night sky. It will be one of the most spectacular astronomical sights in human history. Granted, of course, that life still exists on Earth at that time. However, even when the Milky Way and Andromeda merge, the probability of stars actually colliding remains incredibly low, because space is simply too empty. If you were to shrink the sun down to the size of a ping pong ball, the nearest neighboring star would be hundreds of kilometers away. So a galactic collision is closer to a gravitational restructuring. The entire architecture of the galaxy is slowly reshaped, rather than the explosive, fiery scenes you see in movies. The truly terrifying aspect of the universe is not always its violence. In most cases, its changes are agonizingly slow enough that you can barely perceive them. But as long as you give it enough time, it will still, inevitably, alter everything. And that is precisely why many astronomers share a very poignant saying: the most powerful force in the universe is perhaps not explosions, not black holes, nor even gravity, but rather time. Because time will slowly change every structure. Stars will age, galaxies will collide, orbits will drift, black holes will devour matter. Even the most stable things will ultimately be reshaped by time. And the rotation of the Milky Way, in essence, is also a consequence left behind by time. To understand this, we need to return to a very distant past, back to when the Milky Way was newly born. In those days, the universe was still young. The Milky Way we know today did not yet exist. There was no sun, there was no Earth, there were no spiral arms, nothing but a massive, cold, slowly moving primordial gas cloud. And in the cosmos, almost nothing is ever completely static. Even an exceptionally faint, uneven motion will slowly amplify over time. And so, that cloud of gas began to collapse. And once it started to contract, its rotation speed became faster and faster. This is one of the most foundational laws in the universe: the conservation of angular momentum. You have likely seen a demonstration of this in your youth. a person sitting on a spinning office chair. If they rotate with their arms stretched wide, their speed is relatively slow. But the moment they pull their arms in tight, their spinning immediately accelerates. When the Milky Way formed, the exact same thing took place. As the colossal gas cloud continuously contracted, the originally faint, subtle rotation was amplified, spinning faster and faster, until finally it formed a massive, rotating disc-like structure. And then stars began to emerge. The first generation of stars illuminated the dark universe. Those stars were mostly far more massive than the stars of today. With much shorter lifespans, they burned through their fuel rapidly and exploded, one supernova after another, scattering heavy elements across the galaxy. Later, new stars formed, new planets emerged. Billions of years afterward, the sun appeared, the earth appeared, and life appeared. So in a way, the very reason humanity is able to exist is itself part of the history of the Milky Way's rotation. If the galaxy had not initially formed a stable rotation, the solar system might never have been born at all. And what is more fascinating is that the galactic spiral arms, so familiar to us today, are actually not permanently fixed. They change. Some spiral arms will gradually fade away. New spiral arms will form. Stars will migrate. The entire galactic disk has always been slowly evolving. In fact, the current position where the sun resides today is not necessarily where it has always been. Some studies suggest that the sun may have once been much closer to the galactic center and slowly migrated outward over time. If this is true, it means the environment in which the Earth was born may have been far more violent than it is today. And this kind of stellar migration within the galaxy is actually quite common. Stars do not stay in a fixed territory forever. Gravitational disruptions will alter their orbits. The passing of neighboring galaxies, shifts in the structure of dark matter, and even the spiral arms themselves will all influence the motion of stars. The entire Milky Way is closer to a slowly flowing ocean rather than a static map. Even the solar system itself does not simply stay parked in the dead center of the galactic plane. It slowly bobs up and down, like a horse on a carousel, weaving above and below the galactic disk. Roughly every tens of millions of years, the solar system passes through the densest region of the galactic plane, and some scientists speculate that this periodic crossing may be linked to the evolutionary history of life on Earth. Because within the dense regions of the galactic plane, there are more stars, and gravitational disruptions are much stronger. The probability of comets entering the inner solar system could increase. Certain mass extinction events might be tied to this cycle of galactic motion. Of course, this has not been entirely proven yet, but the concept itself is already quite extraordinary. Many people assume that human history has only been shaped by the environment of the Earth, but that may not be the case. The evolution of life on Earth, from the very beginning, may have been deeply influenced by the movements of the galaxy. In a sense, the history of biological evolution might itself be a chapter within galactic dynamics. And the more scientists study the Milky Way, the more they realize that nothing in the universe exists in true isolation. Everything is influencing everything else. Black holes influence galaxies. Galaxies influence stars. Stars influence planets. Plants influence life. And life ultimately turns around to study the universe itself. It is a deeply strange, beautiful loop. After more than 13 billion years of cosmic evolution, the universe ultimately produced a creature capable of looking up at the Milky Way. And this creature is now beginning to ask, why does the galaxy rotate? Will it ever stop? And will the universe ever come to an end? In a sense, it represents the very first time the universe has begun to analyze its own existence. Of course, these fundamental questions still lack definitive answers today. For instance, what is the true nature of dark matter? We know that the anomalous rotation speed of the Milky Way indicates the presence of significant additional mass, yet the exact composition of that mass remains unidentified. Some researchers hypothesize the existence of undiscovered particles, while others suggest that our current models of gravity may require refinement. Bolder theoretical frameworks even propose that these observations point toward underlying rules within foundational physics that we have yet to uncover. Parallel mysteries are abundant throughout the cosmos. Consider the large-scale architecture of the universe, which organizes into a vast, interconnected configuration known as the cosmic web. On a scale of billions of light-years, galaxies are not distributed uniformly. Instead, they align along colossal thread-like filaments, separated by expansive cosmic voids. This macrostructure represents an incredibly complex system of matter and energy, within which the Milky Way is merely a single node. While this striking geometric arrangement offers profound visual and intellectual insight, the analytical community remains exceptionally cautious, recognizing that structural similarities require empirical validation rather than subjective interpretation. Yet, the scale of this cosmic blueprint remains deeply compelling when examining deep space data, billions of galaxies traversing the quiet expanse, each hosting hundreds of billions of stellar systems, where planetary formations and the conditions for life may naturally occur. This perspective inevitably leads to a question that shapes modern astrobiology. If the universe contains such a vast number of potentially habitable worlds, why have we yet to document definitive evidence of extraterrestrial technological signatures? This inquiry is famously formalized as the Fermi paradox. In 1950, physicist Enrico Fermi raised this pivotal question during a discussion with colleagues, simply asking, "Where is everybody?" The premise is straightforward. If advanced civilizations are a common occurrence in the galaxy, and if even a small percentage developed millions of years ahead of humanity, their physical or technological footprint should theoretically be observable across the Milky Way. Given the vast age of the galaxy, civilizational expansion at even a fraction of light speed would require a relatively brief period on a cosmic timescale. Yet, our astronomical surveys document a profoundly quiet universe, devoid of verified interstellar signals or grand-scale engineering anomalies. To resolve this tension, researchers have proposed various theoretical frameworks, most notably the Great Filter hypothesis. This model suggests that there exists a highly challenging development threshold along the evolutionary path of life, one that the vast majority of civilizations face significant difficulty surmounting. This filter could be situated at the very dawn of biology, implying that the transition from inorganic matter to complex life is an exceptionally rare event. Alternatively, simple life may be widespread, but the leap to advanced technological capability might involve immense systemic risks, such as resource depletion, technological mismanagement, or ecological transitions. The central inquiry for our own species is determining whether this critical evolutionary threshold lies in our past or remains a challenge for our future development. If the filter is behind us, humanity occupies a rare position of opportunity. If it lies ahead, it emphasizes the vital importance of managing our technological maturation with long-term stability in mind. This deep sociological and physical analysis underscores that the parameters required for sustained life are remarkably precise. A civilization requires a stable host star, predictable planetary orbits, liquid water, a resilient climate system, and a sufficient abundance of heavy elements all while navigating localized cosmic anomalies. This is where the long-term rotation and dynamic stability of the Milky Way play a foundational role. The architecture of a spiral galaxy actively dictates the distribution of matter, localized radiation environments, and supernova densities. Certain zones, particularly the chaotic galactic core or the element-scarce outer fringes, present significant challenges to long-term habitability. Our solar system, however, resides perfectly within a balanced region known as the Galactic Habitable Zone. This suggests that the enduring, structured rotation of the Milky Way is not merely an astronomical phenomenon, it is a primary enabling mechanism that provided the necessary time and stability for our own civilization to develop and look back toward the stars. And the deeper we study the cosmos, the more we come to realize stability is actually a rare condition, because the foundational state of the universe is much closer to dynamic instability, galactic mergers, black hole jets, stellar explosions, gamma-ray bursts. Many of these events possess the capacity to instantly disrupt the conditions for life, most notably gamma-ray bursts. This is one of the most intense energetic phenomena in the cosmos, unleashing more energy in a matter of seconds than our sun will output over its entire multi-billion-year lifespan. If a localized gamma-ray burst were to align with Earth, the ozone layer could be significantly degraded in an instant, resulting in a major biosphere event, and human civilization might not even have the opportunity to analyze what had occurred. This highlights the profound nature of the universe. It is not acting with intent against us. It is simply immense, so vast that human civilization appears remarkably fragile by comparison. Yet, remarkably, it is precisely this vulnerability that drives humanity to understand the cosmos with such determination. Because comprehension, in a sense, is our way of navigating the vast unknown. And today, with the advent of the James Webb Space Telescope, humanity has begun to truly observe the earliest generations of galaxies in the universe. These observations are continuously challenging long-held theoretical models. For instance, many early galaxies appear far more mature than previously anticipated. They formed with unexpected speed and contain immense mass. Some even possess structural characteristics that closely resemble modern spiral galaxies. This has led astronomers to consider that our frameworks of early cosmic formation may be incomplete. Furthermore, those newly documented non-rotating galaxies suggest another layer of complexity, that entirely different evolutionary pathways existed in the early universe. Perhaps galactic formation is far more intricate than we ever imagined. And maybe the current architecture of the Milky Way is merely one out of a vast array of cosmic possibilities. Even more extraordinary is that humanity has now achieved the ability to directly image a black hole. In 2019, the Event Horizon Telescope collaboration released the very first image of a black hole. That hazy orange ring of light captured the attention of the entire world, because for the first time, humanity actually looked upon the boundary of an event horizon. Subsequently, Sagittarius A star, the supermassive black hole at the center of our own galaxy, was also successfully imaged. That immense abyss hidden at the core of the Milky Way was finally revealed to humanity. Though the data appears as a soft blur, it nonetheless signifies that humanity can now directly observe one of the most extreme regimes of spacetime. And all of this has unfolded just a little over 100 years since Einstein first introduced the general theory of relativity. In a way, the developmental pace of human civilization is astonishingly rapid. In just a few centuries, we have transitioned from viewing the Milky Way as a faint mist in the sky to actively analyzing galactic collisions, measuring cosmic expansion, imaging event horizons, and surveying exoplanets. We have even begun to model what occurs if a galaxy's rotation diminishes over time. Yet, what truly inspires a profound sense of cosmic scale is rarely any singular discovery. It is what happens when you connect all these insights together. You suddenly realize that humanity exists within an incredibly vast, intensely dynamic, and largely uncharted universe. The Milky Way is not a static backdrop. It is an evolving system in motion. The stars are not permanent lights. They experience birth, maturation, and decline. Black holes are not mere science fiction concepts. They genuinely reside at the cores of galaxies, curving the structure of space and time. And those distant galaxies are not stationary patterns painted onto the night sky. They are drifting apart, interacting, and evolving. Indeed, the entire universe itself is in a state of continuous transformation. In truth, when scientists first discovered that the universe is expanding, many were deeply reluctant to accept it, because traditional human intuition prefers a static cosmos, an eternal, unchanging reality. But that is not the universe we inhabit. In 1929, Edwin Hubble's observations revealed that distant galaxies are moving away from us, and the further away they are, the faster they appear to recede. This demonstrated that the cosmos is not a static stage. It is closer to an unfolding structural expanse. From this foundation, the Big Bang theory was gradually established, giving the universe a defined history, a moment of origin, which also implies that it possesses a future. And today, when we evaluate the concept of a galaxy's rotation altering over time, we are fundamentally discussing how cosmic structures evolve across vast horizons of time. Because nothing in the universe is permanently fixed. Even galaxies are merely temporary configurations held together by gravity. Given enough time, they will inevitably change. And this profound sense of transformation ultimately reshapes humanity's understanding of its own place in the cosmos. In the past, humanity routinely placed itself at the very center of the universe. Later, we discovered the Earth is not the center. The Sun is not the center either, nor is the Milky Way. In fact, even the galaxy itself is merely an ordinary node within the cosmic web. This shifting awareness, in a sense, represents a continuous journey of decentralization. Yet, remarkably, as humanity becomes increasingly aware of its own small scale, we also come to appreciate just how precious consciousness truly is. Because within the currently observed universe, we have yet to document a second civilization capable of researching the cosmos, which means across the entire Milky Way. At this very moment, life on Earth may be alone in pondering why the galaxy rotates. Of course, this does not imply that other civilizations do not exist. The universe is simply too immense. The Milky Way alone may host hundreds of billions of planets. And within the observable universe, there may exist 2 trillion galaxies. This number is so vast that it completely defies human comprehension. If each galaxy holds an average of 100 billion stars, then the number of stars in the cosmos outnumbers every single grain of sand on all the beaches of the Earth. Consequently, many researchers suggest that life could not have occurred only once, but the ultimate barrier is distance. The universe is fundamentally vast. Even the speed of light appears remarkably slow on a galactic scale. For light to travel from one edge of the galaxy to the other requires 100,000 years. Therefore, even if other civilizations exist, they may remain forever separated from one another. The greatest isolation in the cosmos, as many have observed, is not necessarily being alone, but rather that even if others exist, the distances are too grand for an encounter. And at this point, many return once more to that ancient question. Why do we study the universe with such determination? Why does humanity allocate significant resources to build telescopes, research black holes, and search for dark matter? Because from a practical standpoint, these concepts seem entirely removed from daily life. Yet in reality, cosmic research has continuously reshaped human civilization. The global positioning system requires corrections from relativity. Semiconductors originate from quantum mechanics, and wireless communication stems from electromagnetic theory. Many foundational studies that once seemed to serve no immediate purpose ultimately transformed the world. More importantly, astronomy fundamentally alters the way humanity thinks. It reminds us that very little is permanent, not civilizations, not nations, nor even galaxies. Thus, humanity begins to learn to evaluate challenges across expansive horizons of time. And this perspective is exceptionally rare because the human brain naturally prioritizes today, tomorrow, and the immediate years ahead. It struggles to intuitively grasp millions, hundreds of millions, or billions of years. Yet the universe itself operates precisely on these scales. For the solar system to orbit the galaxy once requires over 200 million years. Galactic mergers take billions of years. Stellar evolution spans billions of years. And the evaporation of a black hole could require upwards of 10 to the power of 100 years, a number almost impossible to write out in full. By comparison, the entire history of human civilization is as brief as a passing spark. Yet it is precisely this brevity that makes it extraordinary, because the vast majority of the universe is fundamentally silent, cold, dark, empty. The distances between stars are unimaginably grand. Across vast regions, no noticeable change occurs for millions of years. Yet, on Earth, within a brief window of time, oceans formed, life emerged, consciousness awakened, civilization developed, and technology advanced, until finally, we began to research the galaxy itself, in a sense. This is a remarkable event in cosmic evolution. A primordial gas cloud spins for billions of years to form a galaxy. The galaxy manufactures stars. The stars forge elements. The elements compose planets. The planets foster life. Life evolves into consciousness. And consciousness begins to look upon the Milky Way, to ask, what happens if, one day, the galaxy stops spinning? And perhaps this is where the true fascination of the question lies, because it appears to discuss galaxies, black holes, and the cosmos. Yet in the end, it always leads back to humanity itself, who we are, where we originated, and how long we will persist within the cosmos. Ultimately, we are left with a beautifully simple image. When you look upon the Milky Way late at night, you are not looking at a static pattern painted onto the sky, nor are you looking at a finalized permanent structure. You are witnessing an immense system caught in a state of exceptionally slow transformation, operating continuously far beyond the baseline of human timescales. It will not experience a sudden halt on a specific day, nor will its narrative fracture at a singular moment. It simply continues to exist, continues to rotate, continues to evolve, until an epoch arrives where we can no longer utilize the word rotation to describe it. Therefore, a reduction in rotation is not an abrupt moment that can be definitively observed. It represents the ultimate configuration of a gradual transition. As the stellar density grows increasingly sparse, as the sharp definitions of the spiral arms blur, and as external material inputs diminish, the overarching rotational signature will slowly recede. Yet this decline features no absolute boundary, no point of sudden mutation, no explicit moment of termination. There is only continuous transformation until the galaxy reorganizes into an entirely different structure. And long before any of these variations complete their course, the Milky Way will maintain the exact appearance we observe today. Stable, slow, continuously rotating. Our embedded solar system moves in perfect synchrony within this framework. Because of this, the night sky preserves its familiar patterns, and time itself appears constant. This represents a verified, long-term trajectory. Yet this process is also exceptionally slow, requiring billions of years before entering a phase of visible structural realignment. Prior to that epoch, everything maintains a state of quasi-stability. Rotation persists, structure remains intact, and gravity continues to sustain the overarching morphology. Thus, from our present vantage point, the Milky Way displays no anomalies. It is simply an active, functioning system, residing within a prolonged, stable phase of its evolution. Compressing all of this into a simpler conceptual framework yields a foundational insight. The galactic rotation we observe is not an active event of disruption taking place before us. It is a structurally stable state that has endured and slowly persisted across time. Its transformation is real, but it does not manifest in the form of a discrete event. Instead, it exists as a continuous adjustment, unfolding over immense temporal dimensions. The solar system operates identically within this framework. We revolve around the galactic center, moving with every passing second, shifting our spatial coordinates with every passing year. Yet this movement provides no intuitive sensory feedback. The heavens appear nearly constant, the constellations remain virtually unchanged, and the geometry of the Milky Way displays no visible variation over the span of a human generation. However, if the timeline is extended sufficiently far into the future, all of these structures will gradually alter. The spiral arms will shift, the stars will redistribute, and localized features will undergo stretching or compression. It is just that all of this unfolds on a scale removed from our direct perception. Returning to the macrostructures, the Milky Way is not the solitary system in motion. The entirety of the local group is traversing space. The Milky Way and Andromeda are slowly drawing closer to one another. If we pull our perspective back slightly to a more immediate framework, a simpler reality becomes apparent. The reason we debate galactic rotation, structural transformation, and even far future evolution is not because these changes will abruptly manifest at some critical threshold. It is because the universe itself is a system in continuous evolution. It is simply that the scale of transformation is drawn to extreme dimensions. To humanity, 200 million years is a duration completely beyond sensory perception. Yet to the Milky Way, this represents merely the period required to complete a single, full rotation. Furthermore, the macro reorganization of galactic architecture regularly requires billions of years, or even longer. Consequently, from a practical standpoint, the Milky Way appears entirely motionless, not because it is genuinely static, but because the change is so slow, far too slow to enter day-to-day human experience. Within this specific temporal slice, geometries remain distinct, and star birth remains active. When we look up tonight at the silver ribbon spanning the sky, we are witnessing the universe during an era of peak structural definition, capturing an unparalleled, magnificent snapshot of cosmic history. Stars eventually lose their strict confinement to a singular planar orbit, and their velocity components distribute uniformly across all three dimensions. The collective, orderly fluid flow gradually yields to isotropic pressure support, and the once sharp profile of the galactic disk broadens into a vast, featureless ellipsoid. When the final reservoirs of interstellar gas are fully depleted and new light sources cease to ignite, the system completes its transition, leaving its vibrant spiral era behind forever. This reorientation marks not the erasure of physical matter, but the final conclusion of its macro-scale organization. Emitting only the low-intensity radiation of its remaining red dwarfs, the galaxy functions as a fading ember in the cosmic night, settling into a long period of quiet stasis that spans trillions of years. Yet, humanity occupies a remarkably fortunate position to look upon this vast structural evolution during its most accessible and orderly window. Within this specific temporal slice, geometries remain distinct, and starbirth remains active. When we look up tonight at the silver ribbon spanning the sky, we are witnessing the universe during an era of peak structural definition, capturing an unparalleled, magnificent snapshot of cosmic history. Stars eventually lose their strict confinement to a singular planar orbit, and their velocity components distribute uniformly across all three dimensions. The collective, orderly fluid flow gradually yields to isotropic pressure support, and the once sharp profile of the galactic disk broadens into a vast, featureless ellipsoid. When the final reservoirs of interstellar gas are fully depleted and new light sources cease to ignite, the system completes its transition, leaving its vibrant spiral era behind forever. This reorientation marks not the erasure of physical matter, but the final conclusion of its macro-scale organization. Emitting only the low-intensity radiation of its remaining red dwarfs, the galaxy functions as a fading ember in the cosmic night, settling into a long period of quiet stasis that spans trillions of years. Yet, humanity occupies a remarkably fortunate position. Look upon this vast structural evolution during its most accessible and orderly window. Next, we push this dynamic macro reorganization toward its deepest physical essence. If we evaluate this path through the evolution of phase space and the finality of thermodynamics, it reveals itself as an inevitable transition from a low entropy configuration to a high entropy state. In the language of statistical physics, galaxies initially form highly concentrated, orderly trajectories within the vast six-dimensional phase space, strictly bounded by the constraints of gravity and angular momentum. This concentration along a specific structural plane is, in essence, a low entropy state held in dynamic equilibrium. The complex long-range gravitational perturbations of the broader universe systematically function as a cosmic heat source over immense timelines, steadily injecting randomness into a previously balanced fluid medium. Every instance of a neighboring satellite galaxy passing near our system, and every close gravitational encounter between individual stellar groups, serves to stretch, fold, and dissolve these orderly phase space trajectories. The flat profile of the rotation curve will dissolve, and this structural imbalance will propagate inward, causing the planar disk to gradually reconfigure. The final pathway tracks the slow process of external tidal stripping. Operating within the gravitational environment of the local group, the outer perimeters of the Milky Way face continuous, long-term erosion from neighboring mass fields, systematically drawing fringe stars and gas reservoirs away from the system, reducing the galaxy to a highly compact core over immense timelines as its outer structure dissolves. A comprehensive evaluation of these pathways demonstrates an underlying truth. A reduction in galactic rotation is not a sudden, single event. It represents a continuous structural transformation driven by distinct physical mechanisms, whether through internal orbital realignment, the modification of gravitational support, or ongoing external erosion, all culminating in an epoch where the classic spiral architecture of our galaxy is no longer definable. Yet, this stability remains contingent upon our brief observational window. Across cosmic epochs, the entire system exists as a slowly adjusting process. If these structural parameters deviate from equilibrium, the long-term evolution of the galaxy will reorient along one of three primary physical pathways. The initial pathway involves a merger-dominated structural rewrite, where the Milky Way enters a prolonged gravitational interaction with the Andromeda Galaxy. As the two systems pass through one another, their independent disk geometries will systematically disrupt, scattering orderly planar orbits into randomized trajectories and transitioning the collective structure away from a spiral disk into a uniform, ellipsoidal distribution, where rotation is replaced by isotropic motion. The alternative pathway maps a variation in the architecture of the dark matter halo itself. Should the invisible mass distribution concentrate or disperse significantly, the outer stellar populations, which depend entirely on this gravitational background, will lose orbital stability. Enveloping this visible infrastructure is the expansive dark matter halo, an immense, nearly spherical distribution of unobserved mass that extends far past the visible boundaries of the stellar disk, growing steadily scarcer across distance without a defined perimeter. Without this dark matter envelope, the outer regions of the Milky Way could not sustain their measured velocities, resulting in the rapid degradation of its spiral geometry. In modern astrophysics, the dark matter halo is not an auxiliary hypothesis designed to balance equations. It is a vital prerequisite for the structural existence of the galaxy. Ultimately, the rotation of the Milky Way is the collective statistical summation of multiple overlapping components: the dense gravitational regulation of the central black hole, the visible mass distribution of the flattened disk, the macroscale framework of the dark matter halo, and the continuous presence of localized dynamic perturbations. These parameters combine to project the stable, orderly rotation we document in our modern catalogs. Furthermore, the outer perimeter of this disk exhibits a distinctive structural warp, deviating from an idealized flat plane to bend subtly upward and downward along opposite edges. This geometric distortion is driven by ongoing, long-term tidal interactions with satellite systems, particularly the gravitational pull of the Large Magellanic Cloud, demonstrating that our galaxy does not spin as an isolated, rigid body, but behaves as a responsive structure shaped by external forces. This macro rotation is continuously accompanied by velocity dispersion, the localized, randomized movements of individual stars that superimpose upon the collective orbital flow. This structural randomization arises from multiple stellar processes, including initial kinematic disturbances during starbirth, localized shock waves from supernova events, and long-term gravitational scattering across billions of years. The Milky Way is best modeled not as a rigid rotating platter, but as an orderly macrosystem experiencing continuous internal perturbations. Across the vast expanse of the galactic disk, the rotation curve remains remarkably flat. This flat profile yields a foundational cosmological conclusion. If the mass distribution of the Milky Way were limited to the visible stars and gas clouds mapped in our surveys, this velocity structure would violate fundamental laws of physics. The outer stellar populations would have dispersed into deep space long ago. To preserve gravitational equilibrium, an immense concentration of unobserved mass must envelop the system, establishing the core observational proof for the dark matter framework on a galactic scale. A closer examination of the visible disk reveals a complex stratified thickness. Youthful, high-mass stars and dense molecular clouds are strictly confined to the narrowest thin disk region, whereas older, lower-mass stellar generations distribute across a broader vertical profile, synthesizing a multi-layered, stratified rotational system. It is surrounded by a dense, dynamic environment composed of high-temperature gas reservoirs and sparse plasma streams that revolve around the central mass at high velocities without immediately plunging past the horizon. The core operates primarily as a gravitational regulation center, influencing the inner system kinematics of the galaxy through its dense quality without directly dictating the rotational profile of the distant outer disk. This structure brings us to a primary observational value: the orbital velocity of our Sun around the galactic center, measured at approximately 220 kilometers per second. While this speed appears significant, it sits precisely within a stable, intermediate range for a galaxy of our mass profile. The defining attribute of this velocity profile is that it does not decrease across distance in accordance with standard Keplerian mechanics, which dictate that outer components must travel slower than inner ones due to a reduction in gravitational pull, a pattern clearly demonstrated by the planets orbiting our Sun. While this horizontal expanse is vast, its vertical profile is remarkably constrained. The thickness of the visible stellar disk measures only between 1,000 and 2,000 light-years. In three-dimensional space, our galaxy is an exceptionally flattened structure, where the overwhelming majority of its stars are confined within a narrow, rotating plane. Our solar system is embedded directly within this thin disk, situated roughly 26,000 light-years from the core, a coordinate that is entirely unextraordinary, positioning us as an ordinary point along a standard spiral arm. At the center of this geometry resides Sagittarius A star, the supermassive black hole anchoring the galactic core with a mass concentration equivalent to approximately 4 million suns. Despite its scale, our central black hole does not operate as an intensely active accretion system, maintaining a relatively tranquil activity baseline compared to distant active galaxies. While these three parameters remain satisfied, the galaxy maintains the majestic spiral configuration we observe tonight. As any single component adjusts across deep timelines, the system systematically reconfigures its geometry, navigating a continuous process of structural transformation rather than an abrupt conclusion, until it eventually expresses itself through an entirely different arrangement of cosmic matter. Let us now orient our attention back toward a more localized, empirical framework, focusing on the specific physical parameters that define the structural baseline of the Milky Way. When exploring advanced cosmological models, it is essential to anchor our equations within verifiable physical dimensions, recognizing that all theoretical frameworks must ultimately reconcile with measurable properties. We begin with the physical scale of the galaxy's visible components. The stellar disk of the Milky Way spans a diameter between 100,000 and 120,000 light-years. This reorientation brings us to a more immediate visual summary. The Milky Way we look upon tonight is an open system actively receiving material from the broader cosmos. It is continuously absorbing satellite structures, interacting with gas clouds, and responding to external perturbations. Its rotational architecture remains a dynamic, evolving process. Over immense temporal horizons, however, it will gradually transition into a closed system, sustaining its lingering rotation solely through internal remnants rather than external rejuvenation. Ultimately, all these mechanics can be synthesized into a unified summary. Galactic rotation cannot be modeled as a static attribute, a permanent linear speed, or a simple feature that abruptly appears or disappears. It is the cumulative expression of three foundational mechanisms operating in unison: inward gravitational organization, the absolute constraint of angular momentum conservation, and the continuous influx of material from the external cosmic environment. The Milky Way does not rotate in absolute isolation. It sustains its geometry within a macro-scale network of gravitational flows. Advancing further along this framework brings us to a perspective that closely traces the future evolution of cosmic structures. If the expansion of the universe continues to accelerate across immense timelines, large-scale interactions between independent structures will gradually decrease. The local group will eventually isolate from the surrounding cosmic web, transitioning into a self-contained, closed gravitational system. Within this isolated environment, all subsequent dynamical evolution will rely entirely on internal mass and energy redistribution. As external inputs decline, the velocity of structural transformation will slow, systematically guiding the system toward a phase of dynamical freezing. During this distant epoch, individual stellar systems will continue their independent kinetic movements, yet the macro-evolution of the galaxy will settle into an exceptionally slow baseline. Rotation will persist, but it will function merely as a lingering dynamical remnant of a past era. Its outer stellar boundaries would rapidly decouple from the core, accelerating the transition toward a randomized, ellipsoidal configuration. Therefore, the function of dark matter extends far beyond compensating for missing fringe velocities. It acts as the primary stabilizer of macro-scale cosmic architecture. While textbooks frequently simplify this dynamic into a discussion of flat rotation curves, it remains fundamentally an issue of structural resilience against gravitational collapse. When placed within the grand architecture of the cosmic web, the Milky Way is revealed as a single, localized node, situated along an expansive network of gravitational filaments. A localized concentration of mass within a network of mass filaments, the rotational profile of our galaxy is never dictated solely by its internal mechanics. It remains continuously coupled to the influx of material from the surrounding intergalactic medium. Our system depends on the steady stream of pristine gas flowing along cosmic filaments, the ongoing accretion of minor satellite systems, and the long-term tidal influences of neighboring structures within the local group. This reorientation underscores why irregular galaxies documented in our deep space surveys are highly critical to modern cosmology. They do not represent failed or erroneous stellar systems. They are pristine examples of intermediate configurations captured mid-reorganization, showcasing systems navigating an active dynamical realignment. This distinction remains critical because it permanently alters our interpretation of atypical cosmic structures. Asymmetry does not equal anomaly. Asymmetry equals evolutionary phase. This framework permits a more accurate formulation of the relationship between galactic rotation and dark matter. The surrounding dark matter halo is not merely a mechanism that flattens an observational rotation curve. It serves as the foundational gravitational architecture that permits a structured rotation to persist across vast spatial dimensions. In a universe devoid of this invisible dark matter scaffold, a planar disk system would lack the structural stability required to sustain its orderly rotation over deep timelines following its initial formation. These processes dismantle an organized disk profile with exceptional efficiency because they do not rely on the gradual dissipation of kinetic energy. They systematically rewrite the entire distribution of available orbits. To visualize this process through a terrestrial analogy, imagine a highly organized urban transportation system operating within a dense metropolis. Vehicles flow along established, predictable routes, maintaining a stable, unified circulation pattern across the city. Suddenly, a massive, simultaneous reconfiguration of the entire roadway infrastructure is initiated. All established paths are disconnected, rerouted, and completely redistributed. The consequence of this intervention is not a gradual slowing of individual vehicles, but a total rewrite of the system's overarching flow network. A major galactic merger alters a system on this exact structural scale, moving seamlessly from a highly orderly rotational state to a low rotation profile, and eventually reorienting into a randomized dynamic state. It unfolds as a continuous progression. This mechanical continuity explains why observational astronomy does not define a single abrupt point where a galaxy stops spinning. There is only a gradual, measurable reduction in the proportion of kinetic energy that actively supports the planar structure. Advancing further along this structural framework brings us to a critical but less intuitive mechanism within cosmic evolution: impulsive structural redistribution. This macro-scale reorientation typically unfolds under two primary conditions. The initial condition involves intense galactic mergers. The alternative condition stems from profound tidal disruptions from equivalent mass concentrations. During these massive events, stellar trajectories undergo rapid, collective realignment. The total angular momentum budget is reallocated across the entire system within a remarkably brief window of time. Because in advanced theoretical calculations, research models rarely utilize the macro-term rotation directly, investigators manipulate the specific velocity distribution function, mathematically expressed as f of x, v. This function maps the exact probability configuration of finding a star at a given spatial coordinate x with a specific velocity vector v. When this underlying probability structure displays a prominent axisymmetric and directional alignment across a statistical majority of its components, we observe the macro-scale emergent phenomenon that we classify as a rotating galaxy. Therefore, rotation is not a primary baseline variable. It is a statistically emergent property of an interconnected system, not a fundamental variable. This realization yields a significant structural conclusion. If rotation is an emergent property rather than a primary variable, it does not function as a binary condition that simply exists or ceases. Instead, it operates across a continuous spectrum. If we push this question further to a more ontological layer, a distinct and highly critical reorientation presents itself, one that is easily overlooked. We routinely frame these discussions around whether a galaxy's macro-rotation varies over time. In the precise language of galactic physics, however, a more rigorous formulation presents itself. We are actively evaluating the long-term stability of the phase space distribution function. While this terminology appears more abstract, it represents the foundational mode of expression across entire domains of stellar dynamics. Ultimately, the rotation of the Milky Way is significant, not because it dictates the existence of the galaxy, but because it defines the exact manner in which it exists. The same system manifests as an organized disk under a rotation-dominated regime, transforms into a uniform ellipsoid as rotation diminishes and reduces to a loose gravitational network of dense remnants in the extreme future. The physical components persist, but their organization is entirely reshaped. Human civilization occupies the temporal window, where this architecture is at its most distinct, organized, and comprehensible state, a privilege that reorients our place within the grand timeline of the universe. Furthermore, this transformation does not unfold uniformly across the entire galaxy. The inner core may preserve a tight angular momentum coupling due to the powerful gravitational influence of the central black hole and concentrated gas flows, while the outer fringes grow increasingly disorganized under the steady influence of external tidal forces. The future of the Milky Way involves a stratified regional evolution guided by localized mechanisms rather than a single, uniform change. The ultimate outcome of this journey is a transition away from a rotation-dominated framework toward a randomized dynamic system, where structure is dictated by localized gravitational pockets rather than a macro-scale angular momentum constraint. The galaxy moves away from a single cohesive architecture to become a network of isolated gravitational islands. An organized rotation provides clear velocity gradients, predictable structural symmetries, and definitive boundary conditions for our equations. As these directional signals fade, our capacity to reverse engineer precise mass profiles will decline. The cosmos will effectively become more difficult to decode, not because its underlying physics has changed, but because it will have lost the structural markers that permit analytical reconstruction. Galactic rotation simultaneously coordinates three vital roles. It stabilizes overall architecture, preserves historical data, and functions as a primary source of observational insight. This convergence establishes it as an exceptionally high-value physical phenomenon. It operates as the primary indicator of a galaxy's structural health. While the indicators are clear, the architecture remains organized, information is accessible, and the evolutionary path can be mathematically traced. As the indicators blur, the structure randomizes, and the chronological track becomes increasingly difficult to reconstruct. This irreversibility explains why major galactic interactions routinely culminate in the formation of elliptical systems. The original low-entropy rotational alignment is permanently reconstructed within phase space. To visualize this transformation, imagine a fluid medium where all localized components share highly correlated directional velocities. If an external disruption scatters these pathways, the material continues to move, but its collective, orderly flow is replaced by randomized trajectories. This dynamic highlights why tracking rotation is so critical for observational astronomy. It provides a rare opportunity to reverse engineer total mass distributions from measured stellar velocities. Because we cannot physically weigh a galaxy, astronomers map its velocity field to isolate its gravitational potential, a methodology that provided the definitive proof for the dark matter framework. If the Milky Way systematically transitions into a low rotation phase over immense timelines, observational science will confront a highly practical limitation: a significant reduction in accessible data. When tracking the mechanics of a massive stellar system, physics looks beyond standard three-dimensional coordinates to model a simultaneous distribution of position and velocity. Every individual star is tracked as an active coordinate within a six-dimensional phase space, where three dimensions map its spatial coordinates and three components dictate its velocity vectors. When we state that a galaxy exhibits structured rotation, we are mathematically confirming that its phase space distribution possesses a highly organized, correlated angular momentum framework. Conversely, a reduction in rotation indicates that this orderly distribution is undergoing a long-term process of stretching, mixing, and dispersion. This mechanical reorientation is designated as phase space mixing, and it serves as a primary driver of galactic evolution. Within a collisionless stellar system, this mixing process is fundamentally irreversible. Once the organized alignment of velocities is scattered, the system cannot spontaneously return to a planar rotational profile. When evaluated within the grand chronology of the universe, the position of galactic rotation is remarkably clear. It represents neither the origin nor the final state of matter, but characterizes an intermediate epoch defined by peak structural complexity. This era accommodates the convergence of galactic rotation, distinct spiral arms, active stellar life cycles, and the precise assembly of planetary systems. The overwhelming majority of the structural detail that defines the observable universe is concentrated within this temporal window. The Milky Way we look upon tonight is not a passive background to existence. It represents the universe during its period of maximum structural expression. The eventual reorientation of its rotation is not an absolute conclusion, but a natural transition along an unfolding cosmic path. Delving beneath these structural layers introduces a concept that remains foundational to modern astrophysics: phase space. A galaxy is best conceptualized not as an anchored object, but as an active organizational process, much like a stabilized traffic flow, a localized vortex in a moving stream, or an atmospheric circulation pattern. None of these systems represent static architecture. They are stable configurations sustained by continuous motion. If the underlying flow alters, the structure does not instantly vanish. It systematically transforms its geometry, moving away from a velocity-dominated framework toward a pressure-supported configuration. For modern astrophysics, the primary value of tracking galactic rotation rests on the immense volume of unobserved data it unlocks, serving as our most reliable tool for mapping hidden mass distributions, analyzing dark matter halos, and reconstructing the overarching history of the cosmos. The rotation curve remains a vital asset because it allows us to map the precise influence of components that elude direct visual detection. The increased proportion of unaligned, low-rotation structures in the early universe is not an anomaly. It is a natural characteristic of early structural assembly. This confirms that a non-rotating configuration represents a standard evolutionary phase during the dawn of galaxies. Furthermore, macro-scale rotation is not the solitary pathway that leads to structure formation. It is strictly the outcome of an environment dominated by angular momentum conservation. In alternative cosmic regimes, such as the highly dense centers of massive galaxy clusters, overpowering tidal disruptions can prevent the stable accumulation of angular momentum. Under these intense conditions, a system can bypass the disk phase completely, navigating directly along an ellipsoidal evolutionary pathway. Many galaxies across the cosmos do not initiate their life cycles as planar disks. The architecture of the Milky Way represents a single, stable alternative solution to gravitational equations among a vast array of structural possibilities. Within their scientific framework, this era would likely be classified as a temporary transitional phase. Much like modern physics evaluates the dense plasma state of the infant universe, rather than a permanent baseline for cosmic structures. This realization confirms that humanity does not look out upon a permanent default state of the universe. We are witnessing a specific, temporary observational window. This perspective highlights why the documentation of low-rotation galaxies by the James Webb Space Telescope has generated such significant interest. The breakthrough rests not merely on the telescope's unprecedented resolution, but on its capacity to map high redshift targets. Because light requires vast timelines to span the expanding universe, observing the most distant systems allows us to look directly into the early epochs of cosmic history. Within that infant domain, galaxies are caught mid-assembly before achieving absolute dynamical equilibrium, presenting an environment marked by elevated merger frequencies, rich gas concentrations, and unstable geometries. Under these conditions, the concept of a unified macroscale rotation loses its mathematical utility, because the system can no longer be modeled by a solitary angular velocity. The analytical frameworks must transition away from global fluid continuums toward discrete gravitational network models. This transition marks a profound shift, redefining the galaxy from a continuous medium into a particle-dominated system. The fluid approximations that serve modern astrophysics lose validity because individual stars become functionally isolated, increasing their mean free paths to infinity and rendering macro-scale averages unstable. The remaining angular momentum can only be expressed through statistical distributions across independent objects. If a hypothetical future observer were to evaluate our modern Milky Way from across these vast temporal horizons, they would document an exceptionally orderly, low-entropy system characterized by a stable disk, prominent spiral features, and a precise velocity gradient. Extending this logical progression toward its absolute theoretical boundaries introduces a question that shapes the philosophy of physics. Will our current definition of galactic rotation remain mathematically applicable across the deep future of the cosmos? While this inquiry appears linguistic, it addresses a fundamental property of space-time mechanics. The concept of rotation depends entirely on a specific physical framework, that the system under evaluation behaves as a relatively continuous medium, maintains a distinct boundary, and possesses a definable net angular momentum. Across expansive timelines, these initial parameters will gradually break down. As a galaxy enters the advanced stages of its life cycle, its visible stellar distribution grows increasingly sparse, and its overarching architecture yields to localized gravitational subsystem. The macro-scale dynamics reorient around compact star clusters, binary stellar systems, and isolated structures bound to central black holes. Across deeper timelines, the spiral arms would fade completely, removing any primary structural axis from the night sky and leaving behind a uniform distribution of stars. This transition would not feature an abrupt boundary event or a sudden disruption. It would unfold as an imperceptible gradient across time. Eventually, a point would be reached where human vision could no longer identify the historical spiral architecture that once defined our home in the cosmos. Ultimately, galactic rotation is not a static condition. It is an active process. It links the primordial fluctuations of the early universe to the mechanisms of structure formation and reorients the long-term evolutionary paths that dictate the geometry of our night sky. When we evaluate whether this rotation can alter over time, we are fundamentally examining how cosmic order transitions from organized kinetic movement into a newly established structural equilibrium. This grand process remains in constant, continuous motion. For instance, the cold gas disk aligns most closely with an idealized planar rotation model, whereas the stellar disk displays significant velocity dispersion, and the dark matter halo sustains its geometry primarily through randomized particle orbits. The convergence of these distinct structural layers defines the Milky Way as a complex, quasi-rotational system rather than a uniform, rigid body. This multi-layered framework explains why galactic dynamics remains exceptionally intricate. Researchers are never evaluating an isolated physical object, but rather the gravitational superposition of multiple distinct dynamical systems. If the net rotation of the galaxy were to decrease significantly over immense timelines, the initial changes recorded in our skies would involve a reorientation of our structural perspective rather than immediate shifts in stellar coordinates or stellar brightness. The distinct linear band of the Milky Way would slowly lose its geometric definition. The familiar ribbon of starlight would dissolve, transforming into a diffused, broadened background of starlight spanning the heavens. The alternative branch maps a gradual transition toward an ellipsoidal geometry, where accumulating external perturbations and mergers systematically disrupt the organized rotation of the disk. The final pathway outlines a period of isolated decline, where the internal gas reservoir is fully depleted, star formation drops to zero, and the system enters an enduring era, composed entirely of degenerate stellar remnants. The Milky Way currently occupies the early phases of an evolutionary transition between the first and second pathways. Yet, this reorganization unfolds with extreme slowness, operating on timescales that vastly outlast the existence of human civilization. Furthermore, The rotational profile of the Milky Way does not occur along a solitary idealized plane. It possesses a complex stratified thickness. The independent components of the galaxy, the stellar disk, the interstellar gas disk, and the surrounding dark matter halo, do not exhibit identical rotational behaviors. The second barrier stems from a vast disparity in timescales. The Milky Way requires over 200 million years to complete a single revolution, whereas human astronomical records span only a few decades, a temporal difference exceeding a factor of 1,000,000. The third barrier is driven by localized velocity distributions, where the complex independent motions of nearby stars frequently mask the macro-scale rotation of the collective system. To surmount these obstacles, the scientific community relies on sophisticated statistical analysis and advanced computer modeling, making numerical simulations an indispensable component of modern galactic dynamics. When modeled as a long-term dynamic system, a galaxy's evolutionary path typically reorients along one of three primary branches. The initial branch involves the sustained preservation of the planar disk, an outcome that requires a steady supply of fresh interstellar gas, alongside the preservation of significant angular momentum to fuel ongoing star formation. As interstellar gas clouds travel through the dense corridors of the spiral arms, they undergo compression, triggering the formation of new generations of stars. Simultaneously, through the combined effects of gravitational interactions and large-scale magnetic fields, angular momentum is steadily transferred outward across the disk. This redistribution drives a two-part evolutionary pathway. The inner core regions of the galaxy gradually contract, while its outer fringes slowly expand into a broader geometry. This dynamic is designated as coupled internal-external evolution, and it directly shapes the long-term morphology of the system. Consequently, the rotation of the Milky Way is not a rigid, unchanging spin. It is a slowly adjusting mechanism that continuously reallocates its total angular momentum budget across varying structural layers. This complexity explains why mapping the collective rotation of our own galaxy represents a profound analytical challenge, introducing three distinct layers of observational barriers. The initial barrier involves a fundamental geometric limitation. Because our solar system resides deep within the galactic disk, we cannot obtain an external overhead vantage point. To visualize this process more intuitively, imagine the early universe as a vast, nearly uniform fluid medium experiencing exceptionally subtle, localized disturbances. As gravity initiated the assembly of macro-scale structures, these fluid disturbances were not erased. Instead, they were amplified systematically across immense spatial dimensions. This macro-scale amplification culminated in the grand, slowly revolving whirlpool structures documented in our modern surveys. Galaxies are the direct outcome of these cosmic scale vortices. An equally critical inquiry focuses on the long-term stability of these structures. Can a rotating geometry maintain equilibrium over deep timelines? Astrophysical models confirm that within broad parameters, these configurations are highly stable, though they remain far from static. This stability operates in a statistical sense. For instance, the net directional rotation of an entire galaxy will not spontaneously invert, even as its internal features undergo continuous evolution. The Milky Way functions much like a long-term fluid system, preserving its macro-scale geometry while continuously reorganizing its internal components. A closer evaluation of these internal mechanics reveals a critical but counterintuitive process: the systematic redistribution of angular momentum. Evaluating these conceptual dynamics at a deeper level leads directly to a more fundamental inquiry. If a macro-scale rotation is not an absolute prerequisite for galactic stability, why has it persisted across billions of years? In other words, why does the cosmos display a clear structural preference for configurations that carry substantial angular momentum? This phenomenon does not require a teleological explanation based on intentional design. Rather, it can be clarified through a direct mechanical evaluation of structure formation. The explanation relies entirely on a foundational cosmological concept: primordial density fluctuations. During the earliest epochs of the cosmos, the distribution of matter was not perfectly uniform. Even the most minuscule variations in localized mass density were systematically amplified over billions of years under the pervasive influence of gravity. Throughout this long-term process of gravitational contraction, any initial asymmetry within the collapsing material was preserved and reinforced. This architectural preservation included directional offsets, spatial asymmetries, and localized vortical structures. Therefore, the rotation of a galaxy functions essentially as a mechanical memory of the universe's initial conditions. It is not an arbitrary design feature added to the system during a late stage of development. It was encoded into the very dynamics of gravitational collapse from the dawn of structure formation. Consequently, the rotation of the Milky Way is not perfectly symmetrical. Modern mapping reveals distinct structural variations, such as a prominent warp along the outer perimeter of the galactic disk, where the geometry bends away from a flat plane. This distortion is driven by external gravitational interactions, particularly the tidal influences of satellite systems, like the Large Magellanic Cloud, confirming that our galaxy does not operate as an idealized, isolated system, but as an active structure shaped by its surrounding environment. A reduction in rotation is therefore modeled as a slow dynamical degradation driven by ongoing external disruptions, rather than a sudden event. The defining characteristic of this mechanism is its extreme slowness. For our solar system to complete a single orbit around the galactic core requires between 220 and 250 million years. This scale demonstrates that the entirety of human history is effectively fixed along a minuscule arc of our broader orbit. Our species has never experienced a full galactic cycle, meaning our understanding of these dynamics is derived strictly from the verification of physical laws rather than direct historical experience. If the Milky Way were scaled down to a visible desktop model, the physical movement of our solar system across generations would appear imperceptible. Yet, this localized coordinate dictates the stellar environment we navigate, governing our exposure to nearby supernovas, the density of surrounding interstellar dust, and our frequency of passage through the high-density spiral arms parameters that shape the long-term baseline of our planet. If the galaxy's net rotation gradually decreases across horizons of time, modern astrophysics projects three macro-scale structural transformations. First, the sharp definitions of the spiral arms will slowly dissolve, causing star-forming regions to lose their geometric concentration. Second, available reservoirs of interstellar gas will steadily deplete, lowering the long-term rate of new star birth. Third, the dynamic architecture of the system will undergo ellipsoidization, shifting from an organized disk into a randomized velocity distribution. These adjustments unfold as a continuous background transition rather than an abrupt disruption, remaining completely invisible across human timelines. This profile reflects a primary attribute of the universe. Profound transformations occur across immense temporal dimensions, leaving us with the comforting illusion of absolute stasis during our brief moment under the stars. When we observe the Milky Way, we are looking upon a resilient gravitational system composed of hundreds of billions of stars, navigating a vast dark matter framework, guided by the rules of angular momentum and slowly evolving across immense timelines. The sky we see is a single snapshot frame of an ongoing cosmic narrative, one that appears remarkably stable, yet remains in a state of constant, beautiful flow. Analyzing this intermediate position more deeply reveals an easily overlooked reality. All of our data regarding galactic rotation originates from localized sampling. Humanity cannot obtain an exterior view of the Milky Way's collective movement. Instead, we measure the velocity of our own solar system, record the relative motion of neighboring stars, compile statistical inferences from distant sectors, and carefully piece together a comprehensive model of macro-scale rotation. In scientific methodology, this challenge is classified as an inverse problem. To the process of reconstructing an entire macro-scale architecture from localized observations. Because an inverse problem rarely yields a solitary mathematical solution, our conclusions depend heavily on structural modeling, dark matter distribution models, gas dynamics frameworks, and the foundational assumption that the laws of gravity remain uniform across vast distances. The rotation of the Milky Way is a highly refined conclusion, derived from rigorous physical modeling rather than a raw visual observation. This analytical caution characterizes modern astrophysics, where every concept accepted as secure depends on an interconnected chain of multi-layered inferences. The flat profile of our galaxy's rotation curve remains highly significant because it directly challenges conventional expectations, demonstrating that stellar velocities do not decrease across distance. Had the mass of the Milky Way been limited to visible stars and gas, Newtonian mechanics dictated that outer fringe stars must travel slower than those near the core, mirroring the orbital profiles of the planets within our solar system. The empirical preservation of a flat curve serves as foundational proof for the dark matter halo, transitioning the study of galactic rotation from an exercise in structural astronomy into an active inquiry into fundamental physics. It moves beyond describing how the galaxy moves to address the composition of the unobserved mass-energy budget of the universe. This equilibrium is maintained by an ongoing competition between three structural forces: inward gravitational compression, outward centrifugal velocity, driven by angular momentum, and localized energetic adjustments from gas pressure and stellar feedback. The system maintains a dynamic equilibrium that adjusts continuously over deep timelines. Supernova events redistribute interstellar gas. Central black hole activity alters mass concentrations near the core, and incoming dwarf systems introduce fresh, angular momentum, systematically fine-tuning the galaxy to sustain a quasi-stable rotation. This gravitational coupling prevents the universe from rapidly dissolving into a uniform gas cloud, ensuring instead that structure continuously reorganizes into galaxies, stars, and planets. While individual systems mature and eventually decline, new configurations take shape elsewhere in an ongoing cosmic cycle. The rotation of the Milky Way is simply a stable manifestation of this process. For modern observational astronomy, mapping the galactic rotation curve remains a primary tool because it provides the most direct evidence for the existence of dark matter. In a system consisting solely of visible matter, the velocity of stars on the galactic periphery should decrease noticeably as distance from the core increases. Instead, empirical data demonstrates that the curve remains flat across immense distances, confirming the presence of significant unseen mass. This discovery fundamentally altered our broader cosmological frameworks, establishing the rotation curve as a foundational dataset within modern astrophysics, and proving that galactic rotation is a powerful tool for isolating undiscovered components of reality. This logical progression outlines an interconnected cosmic chain. Galactic rotation stabilizes overall structure, which dictates star formation rates, governs the distribution of chemical elements, directs planetary assembly, and ultimately establishes the environmental baseline required for life. An alteration in any single segment of this sequence reorients the final outcome. Thus, when we evaluate whether a galaxy's rotation can diminish over time, we are ultimately examining if the macro-scale parameters that permit consciousness to emerge are subject to change. Our current astronomical datasets confirm that these transformations unfold with extreme slowness, requiring billions of years to generate measurable structural variations. On the timeline of human civilization, the Milky Way remains entirely stable, even as it navigates continuous transformation across cosmic horizons. Ultimately, the galaxy we look upon tonight is far from a static image or a permanent object. It is an active, dynamical process stretched across time, rotating, evolving, and systematically navigating toward its next evolutionary phase, while we occupy a brief window in the middle of its journey. Consequently, when we state that the Milky Way rotates, we are confirming that the galaxy preserves the dynamic memory of its formation. This is an important realization, demonstrating that our current motion is not dictated solely by modern conditions, but is the cumulative product of billions of years of historical development. This insight introduces a compelling paradox. If angular momentum is conserved, how can a galaxy's rotational profile change over time? The explanation rests on the systematic redistribution of angular momentum. The Milky Way is not an isolated, rigid body. Its constituent stars, interstellar gas clouds, and dark matter continuously exchange kinetic energy and dynamic states through gravitational disruptions, friction, and tidal interactions. Through these internal pathways, angular momentum can be transferred across different sectors of the system. For instance, contracting gas clouds routinely transfer angular momentum toward the core, while outer fringe stars absorb this energy and are propelled into more distant orbits. During major galactic mergers, the entire angular momentum structure of the system can be completely reoriented. Therefore, any variation in galactic rotation is driven by how angular momentum is redistributed within the system, rather than changes to the total budget itself. To map these movements, modern astronomical surveys look beyond single-point velocities to construct a comprehensive velocity field, which charts the exact radial velocity distribution across every sector of the galaxy. A systematic gradient across this field confirms a collective rotation, whereas a highly randomized distribution indicates that the organized rotational structure has diminished or dissolved. The James Webb Space Telescope remains vital because it extends these velocity field measurements into the earliest epochs of the cosmos, where structural systems have not yet attained absolute equilibrium. By documenting an increased proportion of irregular, low-organization galaxies, the Webb telescope provides empirical data on how systems transition from primordial chaos into organized order, rather than merely showcasing the final result. From the standpoint of structural philosophy, galactic rotation serves as a clear illustration of a fundamental cosmic phenomenon, the sustained persistence of localized order. Within a universe governed by a long-term trajectory of increasing entropy, the existence of a highly stable, enduring rotating system might appear contradictory. Yet, the underlying mechanism follows direct physical laws. Because gravity operates as a long-range force, it allows mass and energy to organize cohesive structures over vast dimensions. Following this progression necessitates confronting a somewhat counterintuitive conclusion. Our capacity to debate galactic rotation, structural evolution, and even the eventual fate of the cosmos does not arise because these phenomena are proximate to our experience. On the contrary, it is because the Milky Way happens to occupy an exceptionally stable evolutionary phase. This long-term equilibrium provides a unique observational window, Within astrophysics, this temporal interval is occasionally designated as the resolvable era. This term implies that the system has neither experienced structural collapse nor settled into absolute stasis. Instead, it exists in a state of continuous, measured, and mathematically modelable transformation. Had our system been evaluated in an earlier epoch, such as the high-density phases of the infant universe, the behavior of matter would have appeared far too turbulent, with structures continuously assembling and dismantling before long-term physical laws could be successfully deduced. Conversely, if the system is evaluated in a late-stage epoch, such as the far-future era of black hole dissipation, the absence of structural variation would render dynamical analysis remarkably difficult. It is strictly during this intermediate phase that structure remains sufficiently complex. Transformation unfolds with measured slowness, and the window for observation is sufficiently clear to construct our current scientific framework. The Milky Way resides precisely within this balanced regime, which explains why it serves as a primary focus of modern astronomy. Its significance stems not merely from being our home galaxy, but because it represents a pristine example of structural stability. Evaluating these dynamics at a more foundational layer reveals that the persistence of galactic rotation relies on a fundamental principle of physics, the conservation of angular momentum. This law governs structures across all cosmic scales, dictating that in the absence of an external net torque, the total angular momentum of an isolated system remains constant. While the mathematical formulation is straightforward, its implications for cosmic architecture are profound. When a cloud of interstellar material undergoes gravitational contraction, its physical radius decreases. To preserve total angular momentum, its rotational velocity must increase. This mechanical requirement explains why planetary systems, stellar nurseries, and galactic disks naturally organize into rotating structures. Rotation is not an arbitrarily assigned feature. It is an unavoidable outcome of gravitational assembly. This long-term evolutionary framework reorients what it means for humanity to study the mechanics of galactic rotation. From a scientific standpoint, it demonstrates our capacity to comprehend how gravity organizes complex systems. Methodologically, it highlights our ability to reconstruct deep history through localized data. And cognitively, it confirms that we can successfully infer macro-scale architectures from an internal vantage point. Humanity does not observe the galaxy from an external position. We are embedded within its framework. This locational baseline introduces a unique analytical challenge. We cannot obtain an overhead view of the Milky Way. We must reverse engineer its geometry from a limited internal coordinate, much like attempting to map the exact shape of an entire forest from a single position inside the trees without the ability to observe its perimeter. Astronomers must rely on mapping stellar densities, recording light distributions, and tracking gas velocities to build mathematical models, because a direct external observation remains physically impossible. Ultimately, the rotation of the Milky Way is significant, not because it possesses an intrinsic mystical property, but because it serves as a primary example of structure generation. It clearly demonstrates three core principles of astrophysics: how gravity organizes orderly structures out of primordial chaos, how angular momentum is preserved and redistributed across cosmic scales, and how complex systems maintain long-term stability while continuously evolving. These three tenets form the foundation of how modern cosmology interprets galactic systems, and the Milky Way represents our most direct and observable sample. Therefore, when we evaluate whether a galaxy's rotation diminishes over time, we are not merely forecasting a specific far future event. We are actively investigating a more fundamental question: how order is established, sustained, and eventually reorganized across horizons of time. Humanity occupies a unique intermediate position in this process, fully capable of observing mature structural geometries alongside the subtle markers of long-term transformation long before the system approaches its final conclusion. Gazing upon the Milky Way is not the observation of a static object. It is an active encounter with an unfolding cosmic process. An even more extreme future phase introduces the black hole era. Remaining stars will be gradually disrupted by tidal forces or assimilated by accretion disks, leaving black holes as the primary structural remnants of the cosmos, including the supermassive black hole at the galactic center, alongside countless stellar mass black holes. During this epoch, the concept of galactic rotation becomes increasingly abstract. The system no longer operates as a continuous fluid medium, but rather as a sparse, discrete network of gravitational interactions between isolated, dense objects. The galaxy ceases to resemble a planar disk, manifesting instead as a loose gravitational web. The remaining rotation of the Milky Way transforms into a statistical distribution of angular momentum among independent objects, rather than the sharply defined spiral patterns observed today. Extending our models to their absolute theoretical limits brings us into the deep future of the cosmos. According to prominent theoretical models, black holes will eventually dissipate via Hawking radiation. This process unfolds with extreme slowness, requiring timelines that vastly exceed 10 to the power of 100 years. Once the final black hole evaporates, the universe transitions into the dark era, populated solely by an exceptionally sparse background of photons, low-energy leptons, and dark energy. During this final epoch, gravitational interactions lose the capacity to organize matter, rendering the concept of galactic rotation entirely meaningless because galaxies themselves will no longer exist as structural units. Looking back at our modern Milky Way from the vantage point of this extreme future generates a striking contrast. The rotation we analyze today as a defining feature of cosmic architecture will eventually cease to be a quantifiable attribute because structure itself will have dissolved into a uniform background. In this sense, galactic rotation is strictly a mid-cosmic phenomenon, representing neither the beginning nor the end, but rather an epoch characterized by peak structural complexity. Extending this temporal focus to an even grander macro scale introduces a boundary question that nearly all astrophysical discussions eventually confront. Does this rotational structure of the Milky Way hold long-term significance within the ultimate fate of the universe? In other words, is rotation merely a passing phase, or will it be completely erased in the extreme future? Modern cosmological models offer a distinct resolution. Rotation will not simply disappear, but it will lose its macro-scale significance. This shift occurs because the long-term driver of cosmic evolution is not the localized internal dynamics of individual galaxies, but rather the competition between macro-scale gravitational binding and the expansion of the universe itself. Current observational data demonstrates that the expansion of space is actively accelerating. Driven by dark energy, this large-scale expansion systematically widens the gulfs separating independent galaxies. In the exceptionally distant future, every structure residing outside our local group will recede past the observable horizon, meaning even light will no longer have the capacity to span these expanding distances. From an internal vantage point, the Milky Way will persist, continuing its rotation and maintaining its immediate structure. Yet, from the perspective of the broader cosmos, it will be reduced to an isolated island system, completely severed from informational exchange with external galaxies. Cosmology models this state as the island universe era. During this epoch, each isolated galactic group functions as a self-contained cosmic unit, completely unable to exchange material with external systems or organize into larger structures. Net rotation will still exist within the system, but it will no longer participate in any grander process of cosmic organization. Stepping forward into the subsequent epoch, after all available reservoirs of interstellar gas are fully consumed, star formation will halt entirely. The galaxy enters the degenerate era. During this phase, the internal architecture of the Milky Way consists solely of mature and dead stellar remnants, red dwarfs, white dwarfs, neutron stars, and black holes. The system loses its capacity for luminosity evolution, meaning no newly formed light sources will emerge. The night sky will gradually dim over vast timelines, and while the underlying gravitational structure persists, it will become increasingly difficult to observe. Because these processes unfold across immense timelines, every galaxy captured in our modern deep space surveys appears effectively frozen in time, a single frame of a prolonged narrative. This evolutionary journey directly shapes the chemical development of the galaxy and the distribution of elements. The spiral arms function as high-density zones that accelerate star formation, concentrating the sequence of stellar birth, core collapse supernovas, and the subsequent release of heavy elements. Through the continuous motion of differential rotation, these newly forged elements are systematically mixed with the interstellar medium, establishing a smooth gradient of chemical abundance across the galactic disk. If rotation alters significantly, this mixing mechanism diminishes, causing localized chemical compositions to become fragmented and uneven. Such variations directly impact subsequent generations of planetary formation because the raw materials required to construct rocky worlds depend on the availability and uniform distribution of these heavy elements. Galactic rotation shapes not only the geometry of a galaxy, but also the chemical architecture of its planets and the statistical probability of life emerging across its domains. To determine if a distant galaxy exhibits rotation, astronomers do not rely on visual geometry alone. They analyze its light spectrum. By utilizing the Doppler effect, researchers precisely measure the redshift and blueshift of emissions from opposite sides of the system. If one region displays a trajectory moving toward our detectors while the opposing side recedes, it confirms a collective rotation, mapping a distinct velocity field that reveals the system's rotation curve and confirms the presence of the surrounding dark matter halo. When discovering a potential low rotation system, the scientific community first verifies whether the velocity field lacks a systematic gradient, confirming a state of randomized motion rather than relying on visual classification. With sufficient computational advancement, future astrophysics will likely model these trajectories with high statistical accuracy, since galactic dynamics follow predictable mathematical framework. Given precise data regarding mass distributions, external gravitational fields, and merger histories, long-term numerical simulations can outline a galaxy's structural path. Yet, because galaxies function as chaotic systems, minute variations in initial conditions amplify across deep timelines, limiting our forecasts to statistical pathways rather than exact orbital tracking. A core attribute of cosmic systems, they are entirely comprehensible, yet inherently unpredictable at a granular level. Evaluating the life cycle of the Milky Way reveals three major phases: an initial formation era, where angular momentum accumulates and structure organizes; a mature equilibrium phase, characterized by a stable disk, defined spiral arms, and orderly star formation; and a long-term decline where gas reserves deplete, external disruptions accumulate, and the system gradually transitions toward an ellipsoidal geometry. The Milky Way currently occupies the latter portion of its mature second phase. While it has not entered a period of structural decline, preliminary markers of long-term evolution are already documented, including a gradual reduction in the baseline star formation rate, the ongoing accretion of dwarf systems, and a subtle thickening of the galactic halo. These variations unfold at a velocity that renders the galaxy completely stable across human timelines, presenting a night sky that remains constant to our immediate view while continuously evolving across cosmic horizons. When you look upon the Milky Way tonight, you are not observing a static object. You are witnessing an ongoing process. Every star occupies a temporary coordinate, and every band of light represents the convergence of countless independent orbits. To look at the galaxy is to read a narrative that has unfolded for over 10 billion years, and the story is far from over. For a civilization, the grandest transformations of the universe remain unexperienceable in real time, accessible only through the models of empirical science. This reality generates a primary conceptual tension within modern cosmology. We actively decipher the largest structures in existence while remaining confined to a minuscule snapshot of time. Ultimately, the rotation of the Milky Way serves as a profound symbol mapping how order organizes across time, how architecture sustains against gravity, and how consciousness interprets an expansive universe from a brief vantage point. Evaluating these dynamics at a more fundamental layer reveals the underlying inquiry. Why is rotation so ubiquitous across the cosmic landscape? From planets and stellar systems to entire galaxies, nearly all large-scale structures carry an intrinsic angular momentum. This profile is not an accidental arrangement. It is the direct consequence of the universe's initial conditions. Standard cosmological models demonstrate that the infant universe was not perfectly uniform, harboring microscopic fluctuations in density alongside subtle velocity disturbances. As gravity amplified these variations over billions of years to construct large-scale structures, any initial asymmetry was systematically preserved and amplified by the conservation of angular momentum during gravitational contraction. The universe does not possess an intentional requirement for rotation. It is the natural mechanical byproduct of structural assembly. This explains why a non-rotating galaxy stands out as a unique signature, indicating either an exceptionally rare set of initial conditions or a history marked by intense external disruptions, such as major mergers that redistributed or canceled out the system's net angular momentum. In actual astrophysical simulations, the transition from an organized disk to an ellipsoidal configuration does not occur abruptly. It unfolds as a continuous progression, though certain parameter boundaries trigger clear structural shifts. When rotational velocity can no longer counteract gravitational compression, the system executes a macro reorganization, shifting from rotation support to velocity dispersion support. This structural transition is typically initiated by external disruptions, such as collisions with equivalent stellar systems or the cumulative impact of multiple small accretion events. These interactions systematically introduce kinetic energy into the galaxy's dynamical state, replacing organized orbital paths with randomized trajectories. This reorientation represents a dynamical increase in entropy, and once this randomization crosses a specific threshold, the planar disk can no longer be sustained, resulting in structural reconfiguration. From a purely physical standpoint, a galaxy that completely loses its net rotation can no longer be classified as a disk galaxy, because the definition of a disk requires angular momentum support. If that angular momentum is redistributed or dissipated, the system is dynamically reclassified as an ellipsoidal configuration or a dynamically thermalized system. In this context, thermalization does not denote thermal temperature, but rather that the velocity distribution of the stars has become isotropic, meaning they travel in unaligned directions. These configurations are common throughout the cosmos, defining the architecture of giant elliptical galaxies, globular clusters, and central galactic bulges. These systems maintain gravitational equilibrium without relying on macroscale rotation, sustaining their structures through randomized velocity distributions instead. Thus, within cosmic taxonomy, a non-rotating galaxy represents a standard stable alternative solution to gravitational equations, occupying a completely different dynamical branch than a spiral disk. This distinction directly influences the relationship between galactic structure and the growth of central supermassive black holes. Within a spiral disk, interstellar gas flows along the spiral arms, effectively transferring angular momentum outward and directing a steady stream of fuel toward the core. This mechanical pathway explains why active galactic nuclei are frequently documented within systems displaying prominent rotational features. If this organized architecture dissolves, the mechanisms governing gas transport reorient, shifting the evolutionary trajectory of the central black hole toward a low-activity state or triggering irregular, temporary outbursts. Over long horizons of time, the core environment settles into a low-supply configuration, demonstrating the powerful coupling between macroscale galactic architecture and the evolution of central black holes. A variation in one system inevitably reorients the behavior of the other. Despite these grand transitions, if the Milky Way were to complete its evolution into a low-rotation system, human observers on Earth would perceive almost no immediate change. On localized timelines, the internal dynamics of our solar system are exceptionally stable. The Earth's orbit remains secure. The Sun maintains its trajectory, and the configurations of the stars shift across imperceptible gradients. Noticeable variations in the broader tapestry of the night sky require tens or hundreds of millions of years to manifest visually. If macro-scale rotation diminishes, these structural correlations gradually dissolve. Young stars will no longer gather along defined corridors. Interstellar gas will lose its predictable patterns of compression, and stellar formation will reorient into a randomized, scattered distribution. From the standpoint of information theory, the structural readability of the galaxy decreases. The system still contains an immense volume of data, but it loses its geometric organization. This transition is much like a long narrative losing its paragraph structure. The individual sentences remain intact, but the underlying framework becomes obscured. For observational astronomy, this shift is highly significant because our ability to reconstruct galactic history depends on mapping these orderly geometric patterns. Our capacity to reverse engineer past cosmic events declines as distinctive features like spiral arms, predictable velocity fields, and color gradients fade. Macro rotation dictates not only the visual morphology of a galaxy, but also humanity's capacity to decode its narrative. This reorientation highlights why the James Webb Space Telescope has made the study of low-rotation galaxies so critical. The significance rests not on their absolute rarity, but on our newfound ability to observe them during the earliest epochs of the cosmos. Historically, the Hubble Space Telescope primarily surveyed fully matured systems characterized by well-defined geometries and distinct rotational profiles. The infrared capabilities of the Webb telescope, however, systematically open a window into the infant universe. In that early domain, galaxies are caught mid-assembly, mergers occur with elevated frequency, structures are inherently less stable, and dynamical states operate with significant complexity. Under these conditions, the proportion of irregular, low-rotation systems naturally increases. This does not imply a variation in the foundational laws of physics. Rather, it confirms that we are finally observing unfinished configurations of cosmic architecture. This insight reorients a long-standing assumption by demonstrating that galaxies did not initiate their life cycles in the stable, balanced configurations observed in the modern universe. The early universe was characterized by heightened turbulence, elevated densities, frequent mergers, and massive inputs of kinetic energy. The structural equilibrium displayed by the modern Milky Way is the refined product of prolonged evolution rather than an initial condition. Expanding our focus to an even broader macro scale reveals an easily overlooked reality. The rotation of the Milky Way is not an isolated dynamical event. Instead, it is deeply embedded within a grander architecture, a three-tier coupled system consisting of the dark matter halo, visible matter, and large-scale cosmic structures. Simply put, the galaxy does not spin independently. It is organized and sustained by a vast, surrounding gravitational environment. This distinction is foundational, as common discussions regarding a reduction in galactic rotation often treat the galaxy as a closed system. Yet, the Milky Way has never functioned in isolation. It continuously exchanges mass and energy with its surroundings. Consider the accretion of nearby dwarf galaxies, the influx of high-velocity gas clouds, and the steady replenishment of sparse material from the intergalactic medium. While these interactions appear minor on localized timelines, they systematically reshape the galaxy's mass distribution and angular momentum structure over billions of years. The rotation of the Milky Way is the long-term cumulative product of external supply balanced by internal evolution. Consequently, if astronomers identify a non-rotating galaxy, their primary inquiry does not focus on what the system lost, but rather on deciphering the external history it experienced. This represents a core methodology of modern astrophysics. On a cosmic scale, there are no instantaneous states, only snapshot profiles of long-term evolutionary processes. An equally compelling angle involves the information architecture of the galaxy. If the structured rotation dissolves, how does its internal organization shift? Here, information architecture describes the macro order within the galaxy, including stellar velocity distributions, gas density gradients, chemical metallicity patterns, and the age structure of stellar populations. Within a typical spiral galaxy, these variables are highly correlated. For example, the spiral arms consistently align with concentrations of young stars, while the galactic center hosts an older, high-density stellar population. This arrangement is not coincidental. It is actively shaped by the convergence of rotation, density waves, and stellar formation feedback. Therefore, a low-rotation galaxy is not a cosmic error. It represents one of the standard, mature phases of galactic evolution. The Milky Way simply has not yet reached that stage of its life cycle, remaining within a highly stable, structured spiral phase, a characteristic that directly facilitates the persistence of life. Our system benefits from stable orbits, a low frequency of catastrophic stellar interactions, and a steady production of new stars, parameters that combine to create a resilient habitable window. Yet, this window is a temporary phase on a multi-billion-year scale. The Milky Way will gradually evolve toward an ellipsoidal configuration. Its net rotation will decrease, its disk will broaden, and its stellar population will distribute more uniformly before settling into a long, slow twilight. Because these transformations unfold over timescales that vastly outlast the life cycles of stars or the existence of entire civilizations, humanity's primary relationship to these dynamics is not to alter them, but to observe and decode them. This remains the defining purpose of advanced observatories like the James Webb Space Telescope. They are designed not to change the cosmos, but to permit us to witness its unfolding narrative, capturing the transition from youthful systems to mature structures, from organized disks to uniform ellipsoids, and from sharp definitions to structural dispersion. These grand transitions compose the long-term chronicle of the universe, and the Milky Way is simply a single chapter currently being recorded. And we happen to be situated precisely inside its pages. From our internal vantage point on Earth, the most immediate consequence would be the complete disappearance of the Milky Way band. The distinct ribbon of light we observe tonight is simply the edge-on projection of our galaxy's disk geometry across the sky. Once the disk thickens into an ellipsoid, that clear linear feature dissolves. The night sky would still be populated by stars, but they would be distributed uniformly across the heavens, lacking any primary structural alignment. This reorientation would fundamentally alter human cultural history, because the Milky Way has served as a central architectural axis across centuries of navigation and mythology. Without this prominent celestial feature, the historical frameworks used by early civilizations to conceptualize the cosmos would have followed an entirely different trajectory. This leads to a deeper philosophical question. Is the rotation of galaxies intrinsically linked to the macroevolution of the universe? According to our standard cosmological model, large-scale structures originated from microscopic density fluctuations in the early universe that amplified over billions of years under the influence of gravity to construct galaxies, clusters, and filaments. Rotational motion was not a pre-programmed feature of the cosmos. It emerged as a natural consequence of the conservation of angular momentum during gravitational contraction. The universe does not possess an absolute requirement for rotation. It is a mechanical byproduct of structure formation. This insight confirms that even if macro-scale rotation alters over time, the universe continues its evolutionary journey along a reoriented pathway. This principle explains why elliptical galaxies are so common across modern surveys. They represent mature configurations where original angular momentum has been redistributed or dissipated through historical mergers. Following intense gravitational interactions, the orderly disk geometry is scattered, and the system transitions into a randomized dynamic state. While this concept appears abstract, it can be clarified through a simple mechanical analogy. The Milky Way presently resembles a rotating planar disk. If rotation is removed, the system does not vanish. Instead, its components adjust gravitationally, causing the disk to settle into a thicker, more spherical distribution. The spiral arms dissolve first because their existence depends entirely on differential rotation and density waves. Without rotation, those waveforms cannot be sustained. Subsequently, the star-forming nurseries undergo transformation, as interstellar gas clouds are no longer compressed along predictable boundaries, lowering the rate of star birth and transitioning the galaxy into a quiescent phase. The population of short-lived blue stars declines, elderly red dwarfs become the dominant stellar component, and the collective luminosity of the system decreases. Visually, the iconic, structured ribbon of the Milky Way would fade, transforming into a uniform, diffused background of stars. Yet, an important dynamic must be clarified here. A common misconception assumes that removing a galaxy's net rotation causes its entire stellar population to plunge directly into the central core. In actual orbital mechanics, the process is far more nuanced. Even when collective rotation is absent, individual stars retain their independent kinetic energy and localized velocities. They will not fall inward unless a powerful dissipative mechanism removes their energy. The outcome is a complete reorganization of orbits rather than a total collapse. A more intricate aspect of this scenario involves the behavior of dark matter. Standard cosmological models demonstrate that the invisible dark matter halo forms the primary gravitational scaffolding of the entire galaxy. Even if the visible stellar configuration undergoes a complete reorientation, the overarching dark matter halo remains intact, ensuring the galaxy preserves its macro-scale gravitational boundary rather than dissolving into deep space. The internal components simply adjust to the newly defined gravitational landscape, arriving over immense periods at a new state of equilibrium. This baseline stability would be maintained by pressure support rather than rotational velocity, mirroring the dynamic profile of a globular cluster or the interior of a massive elliptical galaxy. These structures demonstrate that rotation is not the solitary mechanism capable of sustaining cosmic order. It is simply one pathway that yields a specific geometric form. This insight underpins one of the most vital principles of astronomical inquiry. The universe we observe is always shaped by the scales of our instrumentation. Varying dimensions reveal entirely unique systems of order. At a galactic scale, the Milky Way manifests as a grand spiral configuration. At a stellar scale, our solar system operates as a predictable system of orbits. At a planetary scale, Earth displays a highly complex climate framework. And at a biological scale, reality expresses itself through evolution and complex information systems. Every single layer operates according to its own distinct patterns. Yet all these patterns originate from the exact same set of universal physical laws, expressing themselves differently across varying domains. Thus, evaluating whether galactic rotation diminishes over time is fundamentally an inquiry into structural resilience. When a macro-scale system transitions away from its primary mode of organization, can the cosmos successfully sustain its underlying complexity? The current empirical consensus confirms that it can. The expression of that complexity simply alters its form, and this ongoing transformation is far more significant than a simple conclusion. The universe rarely executes an absolute cessation. Its defining characteristic is continuous evolution. If this thought experiment is extended toward a more rigorous theoretical boundary, the inquiry can be reframed. Instead of asking whether galactic rotation will naturally diminish, we can evaluate what occurs if an external mechanism systematically removes angular momentum from the system. In the language of physics, this scenario requires altering the total dynamic state of a structure spanning 100,000 light-years. The mathematical outcome of such a transition is a profound structural reorganization. The primary change involves the immediate dissolution of the classic disk geometry, because a stable galactic disk requires two foundational parameters: significant angular momentum support and gravitational equilibrium. If angular momentum is drastically reduced, stars are no longer required to maintain planar orbits revolving around a central axis. Their trajectories reorient into a three-dimensional randomized distribution, and the system systematically navigates toward a state of dynamical relaxation. The directions of stellar velocities become unaligned, and the thin disk geometry expands into a thick, uniform ellipsoid, a process detailed in galactic dynamics as ellipsoidization through dynamical relaxation. Naturally, the outcome depends heavily on the specific historical trajectory of the system. If a low rotation state was brought about by an intense, violent merger between equivalent galaxies, the early phases of that environment would be highly chaotic and hostile to life. Conversely, if the structure represents a slowly maturing elliptical galaxy that reached equilibrium over immense periods, the localized environment would remain remarkably predictable and calm. The defining factor is not the presence of rotation itself, but the historical process that shaped the galaxy. This distinction remains a foundational principle of galactic astronomy, because a galaxy's geometry is essentially a physical record of its evolutionary past. Rotational velocity, structural definition, gas concentrations, and the age distribution of its stars all function as historical data points left behind across time. Much like geological strata preserve the deep history of the Earth, Galactic morphology documents the evolution of the universe on a macro scale. Consequently, when the James Webb Space Telescope surveys a unique low-rotation early system, the scientific community is not merely cataloging its current features. Researchers are decoding its historical narrative. The structure may indicate a major early merger, an atypical configuration within its dark matter halo, or an entirely alternative pathway of cosmic formation that challenges our current frameworks. Until astronomical surveys secure a broader distribution of data samples, any single explanation remains a preliminary, localized hypothesis. This caution reflects the standard methodology of modern astronomy. As our data grows sharper and more precise, our analytical community becomes increasingly measured in its conclusions. This brings us to a more comprehensive question. If the Milky Way transitions into a low-rotation system over deep timelines, does the universe become structurally simpler? From a purely geometric perspective, it does. The galaxy's architecture moves toward a uniform distribution. The distinct spiral features dissolve, and visible complexity decreases. Yet, from a foundational physical standpoint, the universe loses none of its underlying complexity. The intricate dynamics simply shift from macro-scale arrangements to micro-scale processes. Stellar evolution remains highly complex. The physics of event horizons remains extreme, and the challenge of quantum gravity remains unresolved. Therefore, any perceived simplification is merely a consequence of the scale at which humanity observes reality, rather than a variation in the cosmos itself. An equally compelling inquiry focuses on the central supermassive black hole. If the organized spiral architecture dissolves, how does the core environment respond? Sagittarius A star, the supermassive black hole residing at the center of the Milky Way, possesses a mass roughly 4 million times that of our Sun. It does not exist in absolute isolation. Instead, it is surrounded by a highly dynamic accretion environment where gas, dust, and powerful stellar winds continuously stream inward to maintain a delicate balance. The ongoing supply of this material depends heavily on the broader gravitational architecture of the entire galaxy. If the macro rotation shifts, the velocity and trajectory of interstellar gas clouds will adjust accordingly. Certain gas structures might no longer navigate effectively toward the core, potentially lowering the black hole's mass consumption efficiency and diminishing its localized activity. Simultaneously, alternative cosmological models suggest a completely different outcome. If the structural transition generates significant gravitational instability, vast reservoirs of gas could be redirected toward the center simultaneously. This sudden influx would temporarily amplify the black hole's energetic output, triggering a late-stage eruptive phase. Reorganizations of this scale are well documented in advanced computer simulations, frequently characterizing the interaction phases of major galactic mergers. The luminosity of the central core increases dramatically for a brief period, closely mimicking the characteristics of a quasar. Thus, the supermassive black hole is not the initial driver of rotational variance. It operates as a responsive component to macro-scale structural shifts across the wider system. This reorientation introduces a question of widespread interest. Within a non-rotating galaxy, can biological life continue to exist? Based on our current astrobiological models, the consensus is clear. It is entirely plausible. The critical parameters required for life to emerge do not depend on whether a host galaxy exhibits macro-scale rotation. The primary prerequisites are a stable host star and planets maintaining secure, predictable orbits over billions of years. As long as the local gravitational field accommodates stable planetary paths, biology can theoretically develop and mature. In certain scenarios, a non-rotating or low-rotation stellar environment might offer distinct advantages, presenting a more serene landscape with lower frequencies of supernovas and fewer disruptive gravitational interactions. Over deep timelines, this environmental consistency could provide an optimal habitat for long-term biological evolution. If this single moment is extended across an even grander cosmic timeline, an easily overlooked characteristic begins to present itself. The rotation of the Milky Way is not a uniform, rigid body movement. Instead, it closely resembles a fluid configuration governed by differential mechanics. This reorientation demonstrates that stars residing at varying distances from the galactic center do not share the same angular velocity. This phenomenon is scientifically categorized as differential rotation. The inner regions complete their orbits faster, while the outer sectors follow a slower baseline. It is precisely this variance in velocity that shapes and continuously refines the majestic spiral arms we observe today. If the Milky Way is conceptualized as a rotating vinyl record, the prominent spiral arms are not fixed patterns stamped permanently onto its surface. Rather, they represent concentrated compression zones generated by density waves moving through a revolving medium. Stars continuously travel through these arms, much like a flow of vehicles navigating a localized traffic bottleneck on a highway. They linger within these dense sectors for a prolonged duration, producing an exceptionally bright, closely packed band of stellar systems. Therefore, a spiral arm is not a permanent material structure. It is more accurately defined as a dynamic phenomenon. This detail represents a common misconception regarding the nature of the Milky Way. The brilliant galactic ribbon arching across our night sky is not an anchored star belt. It is the collective visual projection of hundreds of billions of stars tracing independent orbital paths. If the Milky Way were to alter its rotational velocity over long timelines, this differential mechanics would be the first to dissolve. The spiral arms would lose their sustaining force. The density wave mechanism would cease to function, and the overall stellar distribution would gradually become more uniform. Yet, this process would not unfold instantaneously. Because individual stars possess immense orbital inertia, they would continue to trace their established paths for vast periods. The primary change would involve the gradual reorganization of the galaxy's overarching structure. From this analytical standpoint, a shift in rotation is more accurately modeled as a reorientation of the system's structural integrity rather than a cessation of physical motion. Synthesizing these insights yields a clear developmental model. The Milky Way is currently navigating its mature, middle-aged phase. Its architecture remains resilient, and its rotation is well-defined. Yet subtle markers of change are gradually accumulating. The long-term star formation rate is adjusting downward, available gas reserves are being consumed, and localized external mergers are slowly approaching. The future trajectory of our system is already partially outlined by foundational physical laws, yet the specific structural details remain open to variance. This characteristic defines the enduring appeal of cosmological research. It presents an arena guided by predictable mechanics, yet populated by complex variables. We can map orbital trajectories with mathematical precision, yet we cannot completely forecast the historical outcome of entire galaxies. The cosmos operates much like a flowing river. We comprehend its underlying fluid dynamics perfectly, yet we cannot specify the future coordinates of every individual droplet. Returning to the foundational inquiry, what does it imply if the Milky Way stops rotating? From a rigorous physical standpoint, it signifies a major reorientation of structural dynamics. From an observational perspective, it involves the dissolution of spiral features and the macro-scale reconfiguration of galactic geometry. From a chronological viewpoint, it marks the conclusion of a prolonged evolutionary epoch. Yet, from a human perspective, the thought experiment operates primarily as an analytical reminder. It reminds our species that the galaxy we look upon tonight is far from a permanent static backdrop. It is an immense, evolving system in constant motion. Every stream of starlight we detect, every recorded stellar coordinate, and every completed rotation represents a single passing frame within the deep history of the cosmos. And humanity happens to occupy a unique temporal window that permits us to stand amidst this frame and interpret the grand architecture of reality. From the internal vantage point of our solar system, the immediate impacts will be indirect. The solar system is a localized structure, and a macro-scale shift in galactic dynamics will not instantly alter our local orbital stability. Over deep timelines, however, the changing distribution of neighboring stars will alter the stability of the Oort cloud, increasing the frequency of gravitational disruptions and potentially altering the rate of comets entering the inner solar system. Yet, these variations operate on scales of hundreds of millions of years, remaining entirely imperceptible across the life cycle of a human civilization. This illustrates a primary attribute of the cosmos. Its structural transformations are real, yet they unfold far beyond the baseline of human experience. From a broader perspective, galactic rotation serves to preserve a system's structural memory. It maintains the disk geometry, sustains the spiral arms, and dictates the balanced distribution of star-forming environments. Once rotation is significantly reduced, this structural memory undergoes a gradual degradation. The galaxy transitions into a more uniform state, but this uniformity does not imply simplicity. Rather, it represents an increase in localized structural randomization. In the context of statistical mechanics, this reorientation describes a transition from a low entropy configuration to a state of higher entropy. Within cosmic parameters, this trajectory is practically irreversible. This irreversibility underscores why galactic rotation remains so vital. It functions not merely as a description of kinetic movement, but as a primary source of architectural stability. From a macro-scale perspective, rotation maps closely to the broader life cycle of galaxies. Younger galaxies routinely exhibit heightened kinetic activity, prominent rotational dynamics, and sharply defined geometries. Middle-aged galaxies achieve a state of relative equilibrium, where rotation remains highly distinct, but structural interactions begin to introduce complexity. Elderly galaxies complete their transition toward ellipsoidal structures, displaying a reduction in collective rotation and randomized stellar orbits. Regardless of the underlying mechanism, the outcome redefines the system's structural equilibrium. The galaxy deviates from a stable, rotating disk and transitions into a randomized geometry. Stellar trajectories shift from organized planar orbits to isotropic ellipsoidal paths. The distinct spiral arms dissolve, the disk thickens, and the system organizes into a uniform stellar cluster. In astronomical classification, this marks the transition of a spiral system into an elliptical galaxy, moving from an organized, rotating framework to a thermalized system devoid of a primary direction of motion. The process is driven by dynamical heating. When a galaxy undergoes intense gravitational disruptions, the kinetic energy reorients the star's paths, causing their velocities to randomize and systematically reducing the net rotation of the collective system. This does not mean the stars cease their motion. Rather, their orderly revolution transforms into unaligned trajectories. Much like a stirred cup of coffee after the central swirl dissipates, the individual elements continue to move, but their collective direction is randomized. On a galactic scale, the visual transformation would be profound. The well-defined ribbon of the Milky Way will gradually dissolve, losing its distinct silver-white contour as its stellar population disperses uniformly across the sky. The celestial landscape will lose its iconic line of starlight, taking on a diffused, thick distribution of stars. This alteration will be directly apparent to human vision, because the familiar Milky Way band is simply the projection of our rotating disk geometry across the sky. Without rotation, that projection ceases to exist. Humanity happens to exist during this window of maximum structural stability. This specific temporal position permits us to observe active starbirth, map distinct galactic geometries, and survey the deep past of the broader cosmos, a vantage point that is far from permanent. An era situated billions of years earlier would have presented an environment too turbulent to navigate, while an epoch situated billions of years later will face a night sky marked by isolation and silence. The present offers an optimal window, and it is within this parameter that human civilization has formulated a profound thought experiment. What happens if the galaxy stops rotating? The inquiry demonstrates that humanity has transitioned from passive observers to analytical entities attempting to decode the foundational mechanics of the cosmos. Even when the distances are grand and the answers reside across vast horizons, the determination to model these dynamics remains an intrinsic characteristic of a mature civilization. From a strict physical standpoint, an established galaxy cannot experience an abrupt, sudden halt. The conservation of angular momentum operates as an absolute rule. Rotation is not a mechanical feature that can be deactivated, but an intrinsic, cumulative property of the system's mass distribution. Much like a massive disk spinning on frictionless ice, it will maintain its motion indefinitely, unless acted upon by an equivalent external force, slowing only across intense timelines as its structural order evolves. Consequently, if astronomers were to document a massive galaxy devoid of rotation, it would indicate that the system experienced an extraordinary historical event. Such a profile implies a violent merger with an equivalent mass concentration, a profound reorientation of the local dark matter halo, or gravitational dynamics that challenge our current physics. Our solar system might be propelled toward the distant perimeter of the combined structure, drawn closer to the newly unified core, or launched into the intergalactic void as an independent rogue system. Over subsequent billions of years, the two structures will merge into a single, massive system, widely designated as Milky Way. While this outcome represents a profound structural reorganization that dismantles the classic spiral configuration, the initial compression of gas clouds will trigger a temporary surge in star formation, brightening the collective landscape before the system gradually settles into a stable elliptical geometry across even grander horizons of time. This newly unified galaxy will continue to interact with neighboring systems, eventually entering the advanced epochs of cosmic history, where the broader universe dims, star formation halts, and active stellar life cycles reach a baseline conclusion. The remaining material universe will consist primarily of degenerate stellar remnants, white dwarfs, neutron stars, and black holes surrounded by a sparse field of radiation, navigating an exceptionally slow evolutionary phase that approaches absolute stillness. Yet, our modern surveys observe the Milky Way during an exceptionally active and balanced phase of its history. Its spiral arms are sharply defined, its stellar density is stable, its molecular clouds are productive, and its central black hole operates in a quiet equilibrium. The galaxy occupies its mature era, situated between its turbulent formation and its distant decline, an evolutionary progression shared by natural systems across multiple scales, moving from assembly and activity to equilibrium and eventual reduction. Yet a galaxy does not cease to exist when it reaches this phase. It persists across intense timelines, operating in a low-energy state, where stellar interactions decrease, energetic disruptions diminish, and the entire system achieves a long-term structural equilibrium. While this represents an aging process from a dynamic standpoint, it signifies structural endurance across cosmic time. The Milky Way is destined to follow a similar trajectory, though it must first navigate a major gravitational interaction. The merger with the Andromeda Galaxy. Astronomical data confirms that Andromeda is approaching our system at roughly 110 kilometers per second on a direct gravitational trajectory. In approximately 4 billion years, this interaction will fundamentally reorient the night sky as Andromeda expands across the field of view to form a prominent, rotating concentration of starlight far more pronounced than our modern moon. As the two systems pass through one another, direct impacts between individual stars remain highly improbable due to the vast emptiness of interstellar space. Yet their orbital trajectories will be completely reshaped. Amidst this unfolding chronology, the rotation of the Milky Way serves as the constant mechanical background of the entire arena. Regardless of the emergence or decline of individual civilizations, the life cycles of stars, the movements of black holes, or the eruptions of supernovas, the galaxy maintains its slow, measured revolution like a massive clockwork system spanning billions of years. Long after our current epoch has transitioned into geological history, the Milky Way will continue its rotation. Its spiral arms will span the dark, and newly developing stellar systems will organize, perhaps fostering independent lineages of consciousness. On a cosmic scale, a technological society may represent a temporary marker in the dark, yet its brevity highlights its value. If we extend our chronological focus across expansive horizons of time to a scale that challenges conventional descriptions, the future trajectory of the Milky Way involves a gradual stabilization. The system will slowly and steadily lower its overall activity, beginning with a decline in the rate of star formation. Presently, the galaxy manufactures stars continuously, utilizing the vast reservoirs of cold hydrogen gas concentrated within its spiral arms. As gravity drives these clouds to contract, new stellar systems ignite. Yet this fuel source is finite. The interstellar medium does not receive infinite replenishment. Its reserves are consumed systematically as gas is integrated into stars, dispersed by supernova winds, or drawn past the event horizons of black holes. Over deep timelines, the Milky Way will experience a reduction in available gas. The birth of new stars will grow increasingly rare, and elderly, low-mass stars will dominate the galactic population. The night sky will lose its high-mass blue stars, shifting its primary spectrum toward a subdued, long-lived red. This transition characterizes mature galaxies throughout the universe. The massive elliptical systems documented in our deep space surveys have completed their primary star-forming phases, consisting almost entirely of elderly red dwarfs and cooling white dwarf remnants. Conversely, many astronomers maintain a measured, objective optimism, recognizing that the sheer magnitude of the galaxy is sufficient to explain the lack of contact. The distances separating independent systems are vast. Even if multiple technological societies exist simultaneously, the logistical boundaries of spacetime make interactions exceptionally difficult. The Milky Way spans roughly 100,000 light-years in diameter. Even an information packet traveling at the absolute velocity of light requires 100,000 years to traverse the system, a duration that outlasts the entirety of recorded human history. Cosmic distance itself functions as an effective barrier to communication. The earliest radio emissions generated by human technology have traveled just over 100 light-years into space, representing a minuscule ripple on the surface of a vast galactic ocean. The overwhelming majority of the Milky Way remains entirely unaltered by our presence, unaware that our civilization exists. From this perspective, humanity has only just initiated its preliminary signals. Tens of thousands of years from now, a distant observational system might record our early broadcasts for the first time, receiving low-resolution analog data mixed with interstellar noise. This transfer of information emphasizes that observing the universe always involves looking into the past. If an independent civilization were surveying Earth at this moment from a distance of 65 million light-years, their instruments would record the final epoch of the dinosaurs rather than modern human infrastructure. At a distance of several thousand light-years, the light reaching their detectors would predate the rise of our earliest cities. A synchronized timeline does not exist across the cosmos. Every region observes the history of the surrounding universe rather than its current state. Under this model, civilizations across the cosmos exist without mutual trust, encounter significant barriers in verifying intentions, and compete within an environment of finite resources, making concealment the safest operational strategy. A society refrains from broadcasting because the motivation of a responding entity cannot be predicted. While this perspective aligns with certain game theoretic models, it remains a philosophical framework rather than an empirically verified fact. Its prominence stems primarily from how directly it addresses a profound question: the enduring silence of the cosmos. Our modern surveys have successfully verified thousands of exoplanetary systems, confirming that worlds matching the Earth in physical size or residing within a host star's habitable zone are not uncommon. Given that the Milky Way contains hundreds of billions of stars, statistical models indicate that the conditions for life should be distributed across the galaxy. Yet, the primary contradiction remains. If biology and technological developments occur regularly, why does the interstellar medium appear entirely vacant? This tension defines the Fermi paradox. In 1950, physicist Enrico Fermi raised this fundamental question during a discussion with colleagues, simply asking, "Where is everybody?" The inquiry has since become one of the most prominent puzzles in modern science and philosophy. One school of thought suggests that technological civilizations frequently succumb to internal risks before achieving interstellar capability, such as unmanaged resource depletion, runaway artificial intelligence, or large-scale conflicts. Under this framework, technological maturation advances faster than a species' capacity for systemic self-regulation. An alternative model introduces a colder mechanism, the Great Filter. This theory posits that there exists an exceptionally difficult developmental barrier along the evolutionary path of life, one that the vast majority of civilizations fail to surmount. The primary question for our own species is whether this critical threshold lies in our evolutionary past or remains a challenge for our future development. If the filter is behind us, the transition from simple life to complex technological capability is a rare anomaly, implying that humanity occupies a unique position of opportunity. If the filter lies ahead, it indicates that advanced societies regularly encounter a systemic barrier that precludes long-term survival. This postulation serves as far more than a commentary on potential extraterrestrial life. It directly challenges our projections for the long-term trajectory of human civilization. Another subtle alternative presents itself. The galaxy may not be quiet at all, but rather human sensory and analytical frameworks remain too rudimentary to decode its activity. This hypothesis has run parallel to the advancement of modern observational astronomy. In 1960, astronomer Frank Drake initiated the first systematic, empirical attempt to detect signals from an extraterrestrial civilization, an endeavor designated as Project Ozma. Using a radio telescope to survey nearby stellar targets, Drake monitored specific frequencies in the hope of documenting an artificial transmission. This milestone marked the formal inauguration of the SETI initiative, the search for extraterrestrial intelligence. Although that initial survey yielded no anomalous data, it introduced a new era of research. From that point forward, the scientific community began to rigorously analyze how an independent technological society might communicate across cosmic distances. Would they utilize radio frequencies, focused laser radiation, neutrino emissions, or alternative physical mechanisms that human physics has yet to conceptualize? The underlying challenge rests on the remarkably brief history of human technology. Our utilization of radio communication spans little more than 100 years, while our modern digital era accounts for a mere fraction of that time. If the Milky Way hosts civilizations that progressed millions of years ahead of our current baseline, the technological disparity would not resemble the gap between ancient and modern humans, but rather the cognitive distance between an ant and a human researcher. Furthermore, advanced societies might purposefully choose to forego active broadcasting, because disclosing a planetary location carries inherent strategic risks. This concept is the core premise of the dark forest hypothesis. Modern instruments routinely map event horizon shadows, record gravitational ripples, and analyze the relic signature of the cosmic microwave background. Yet, foundational questions remain unresolved. Why did the universe originate? How did time initiate? What preceded the Big Bang? Indeed, the term Big Bang itself is simply a model for the initial expansion of space-time, because the concept of before may lose all mathematical meaning prior to the emergence of the cosmic fabric. Time itself is an intrinsic component of the universe. Encountering these concepts frequently inspires a sense of intellectual disorientation. The human brain evolved to manage localized variables necessary for terrestrial survival, navigating short distances, evaluating velocity, managing immediate hazards, and securing resources. Faced with cosmic dimensions, our evolutionary intuition encounters absolute limits. Spans of billions of years, populations of hundreds of billions of stars, and distances of millions of light years cannot be naturally visualized. They must be managed through the abstract frameworks of mathematics and physics. Consequently, cosmological study inspires a unique emotional baseline, one marked by a sense of small scale, balanced by a deep intellectual peace. Recognizing the magnitude of the galaxy places immediate daily anxieties into a measured perspective, highlighting their brief duration. This insight does not diminish the value of human life. Rather, it underscores its significance. The Milky Way has rotated for over 10 billion years and will continue its journey across expansive horizons of time. Our history occupies a fraction of a moment within this timeline. Yet within this brief window, our species has constructed advanced observatories, decoded stellar life cycles, mapped extreme gravitational regimes, and modeled the far future trajectory of the galaxy. This capacity is extraordinary. The universe does not actively broadcast its underlying principles. Every milestone of scientific literacy represents the steady, cumulative effort of generations. Investigators formulate mathematical systems, map gravitational mechanics, build advanced instrumentation, and systematically decipher the light of distant stars. Through these individual contributions, the research community gradually constructs an accurate model of the cosmos. The Milky Way is far more than a collection of stellar systems. It serves as a mirror for human curiosity. Every instance of looking up at the stars confirms an intrinsic drive within our species to comprehend the far reaches of reality. This impulse marks the true transition into a technological society, the moment a species moves beyond basic survival to evaluate what lies past the boundary of its atmosphere. Our narrative spans thousands of years, traveling from ancient campfires to modern radio observatories, and from mythological interpretations of the night sky to precise deep space data. Humanity has successfully reached out to touch the perimeter of our home galaxy. And the primary lesson of this journey is that the horizon of the unknown remains vast. When the night sky is completely still, it is easy to experience the illusion that the cosmos is entirely motionless. The positions of the stars appear permanent, yet the entire galaxy is actively traversing space at remarkable velocities. Our solar system travels around the galactic core at roughly 220 kilometers per second, requiring approximately 230 million years to complete a single orbit, a duration designated as one galactic year. The last time our system occupied its current galactic coordinates, modern human civilization did not exist. Early dinosaurs navigated the primordial biomes of Earth. The temporal mechanics of the galaxy operate completely outside the parameters of human intuition. Furthermore, the Milky Way itself is in motion through the intergalactic medium, traveling toward a specific sector of space at approximately 600 kilometers per second. This trajectory is shared by the neighboring systems of the local group. And on an even grander scale, the entire Virgo supercluster participates in this macro-scale movement. The galaxies drift like currents across an expansive, shifting cosmic ocean. At times, researchers document anomalies within these macro movements that challenge conventional explanations. Early cosmological data suggested that a vast array of cluster systems appeared to flow toward a specific, distant region of space, a phenomenon tentatively designated as dark flow. Some theoretical models evaluated whether an immense concentration of mass residing beyond our observable horizon was exerting a powerful directional gravitational pull. While this hypothesis remains a subject of ongoing debate and rigorous validation within the scientific community, it serves as an important reminder that our observable horizon does not encompass the entirety of reality. Humanity is limited to surveying the observable universe, a boundary defined by the age of the cosmos and the velocity of light. Because light requires time to span the gulf of space, we can only detect emissions that have had sufficient time to reach our instruments since the dawn of cosmic history. Beyond this observational perimeter, countless galaxies may exist, permanently removed from human contact, not due to technical limitations, but because the foundational laws of physics preclude the transfer of information across expanding space. This ultimate boundary demonstrates that empirical knowledge may encounter absolute horizons. The Milky Way sits within a small sector of this immense, unmapped reality. The study of galactic rotation also altered our perspective on cosmic stability. Historically, the universe was conceptualized as an unchanging clockwork mechanism, orderly, silent, and permanent. Subsequent data revealed a far more dynamic environment, characterized by galactic mergers, stellar systems interacting with central black holes, supernovas, and the continuous life cycle of stars. The Milky Way exists in a state of constant structural transformation, unfolding on timescales so immense that it appears entirely static across a human life. If the entire evolution of our galaxy were compressed into a single 24-hour day, the span of human civilization would occupy less than the final second. The agricultural era, the Industrial Revolution, and the modern digital age milestones that redefine our human experience disappear into a fraction of a moment on a galactic scale. Yet, it is precisely this brief duration that highlights the significance of consciousness. Within the multi-billion-year timeline of galactic rotation, a conscious species has successfully emerged, organized the tools of empirical inquiry, and become aware of the galaxy's existence. The cosmos hosts trillions of stars, yet the alignment of parameters required to foster life capable of analyzing the night sky remains rare. Technological civilizations may represent an exceptionally low probability outcome, an insight that forms the unsettling core of the Fermi paradox. If the universe features the conditions for life to evolve regularly, why does the interstellar medium remain silent? Various models address this question, with some suggesting that civilizations face inherent risks of self-destruction, others pointing to the immense logistical barriers of interstellar travel, and some postulating that advanced societies eventually transition into digitized environments, abandoning physical expansion. Alternatively, a more isolated possibility exists, that at this moment, the Milky Way harbors no other technological societies. This hypothesis is simultaneously sobering and profound, because it implies that across hundreds of billions of stellar systems, Earth is uniquely home to life, capable of conceptualizing the universe. Under this framework, the responsibility of human stewardship extends far beyond terrestrial concerns, for humanity serves as the temporary lens through which the galaxy observes itself. When evaluating the specific mechanics of galactic rotation, one of the most critical figures was Vera Rubin. Her meticulous data would eventually reorient modern cosmology. During the 1970s, Rubin initiated a comprehensive survey of galactic rotation velocities. According to classical Newtonian physics, stars residing further from the dense galactic center should exhibit slower orbital velocities because gravitational pull diminishes across distance, a dynamic clearly illustrated by the outer planets of our solar system traveling slower than the inner ones. Yet, empirical observations revealed a completely different profile. Rubin documented that the orbital velocity of stars on the galactic fringe did not decrease. Instead, their speeds remained remarkably consistent. The stars traveled at velocities so high that, according to visible mass calculations, they should have been flung into intergalactic space long ago. Because they remained securely bound within their systems, researchers deduced that an immense volume of unobserved mass must exist, providing the additional gravitational force required to maintain equilibrium. Through this structural analysis, the hypothesis of dark matter entered mainstream scientific consensus. To this day, dark matter has not been directly isolated. Yet the rotational profile of the Milky Way serves as foundational evidence of its presence. This illustrates a primary methodology of modern astrophysics. Researchers frequently confirm the existence of a phenomenon not through direct visual observation, but by precisely measuring its systemic influence on the surrounding environment. Much like observing the movement of leaves to confirm the presence of wind, astronomers evaluate the flat galactic rotation curve to confirm the structural envelope of dark matter. Without this invisible gravitational framework, massive, stable, spiral galaxies could likely never exist. Their outer stellar populations would have dispersed across deep space long ago. The structural integrity of our host galaxy depends primarily on a component whose exact composition remains unidentified. Humanity resides inside a system whose primary mass component eludes direct sensory detection. Furthermore, this mystery is merely a localized segment of a far more expansive array of universal unknowns. Many cosmologists acknowledge that our current models encounter a unique conceptual challenge, because the two most influential drivers of macro-scale cosmic architecture, dark matter and dark energy, are still not fully understood. The scientific community maps their behavior and balances cosmological equations around them, yet their foundational nature remains unresolved. This pattern regularly guides the advancement of science. Empirical data exposes a phenomenon, and subsequent generations slowly decode its underlying physical principles. Human understanding of galactic rotation is a relatively recent development. Modern society often takes it for granted that the Milky Way revolves. Yet a little over 100 years ago, the scientific community could not even confirm the foundational nature of our galaxy. During that era, our empirical knowledge of the macrocosmos remained strictly limited. A prominent school of thought among astronomers suggested that the Milky Way composed the entirety of the universe, and the faint, blurry nebulae documented in the night sky were merely minor, localized structures within our own galaxy. This model shifted fundamentally following a pivotal milestone in astronomical history. In 1920, the Smithsonian Institution hosted a historic debate that reoriented our understanding of reality, the Great Debate. The central inquiry focused on a single question: were the spiral nebulae separate, independent stellar systems? One perspective maintained that the universe was relatively small, with the Milky Way encompassing nearly all of existence. The alternative argument proposed that these nebulae resided at profound distances, functioning as independent galaxies. Ultimately, Edwin Hubble provided the empirical verification. By analyzing Cepheid variable stars within these systems, Hubble calculated that the Andromeda Nebula resided far beyond the physical boundaries of the Milky Way. This measurement confirmed that Andromeda was not an internal celestial object, but an entirely separate galaxy. Instantly, the documented scale of the cosmos expanded significantly, and humanity recognized for the first time that the Milky Way was merely one system among an immense population of galaxies. A paradigm shift of the same magnitude as realizing the Earth was not the center of the solar system. Had the galaxy maintained a highly chaotic, non-rotating architecture from its inception, our solar system might never have organized, the Earth would not have formed, and humanity would not exist. The ability of modern humans to sit quietly, observe the night sky, and model the mechanics of the galaxy represents an exceptionally rare configuration of conditions. The overwhelming majority of the universe presents environments entirely unsuited for biology, characterized by absolute vacuum, intense radiation fields, extreme thermal gradients, and profound darkness. Yet, along the perimeter of a single spiral arm, within this vast expanse, an ordinary planet developed oceans, sustained life, and fostered consciousness. The fact that this consciousness can now turn inward to decipher the very rotation that created it stands as one of the most remarkable milestones in cosmic evolution. Astroengineers have evaluated the concept of a stellar engine, a macro-engineering structure designed to control a star's directional emissions, to slowly alter the trajectory of the entire stellar system. While this scale of engineering resides entirely outside modern human capability, it demonstrates that to a highly mature civilization, stars themselves might function as manageable resources. This model aligns with the Kardashev scale, a method used to categorize a civilization's technological advancement based on its energy consumption. A Type 1 civilization utilizes the total energy profile of its home planet. A Type 2 civilization harvests the complete energy output of its host star, and a Type 3 civilization commands the energy resources of its entire galaxy. Humanity has not yet attained Type 1 status, but if more ancient societies persist within the Milky Way, they may execute engineering projects on a galactic scale, adjusting stellar trajectories, harvesting energy from event horizons, or organizing stellar layouts to maximize efficiency. While empirical evidence has yet to confirm the existence of such advanced entities, evaluating these possibilities demonstrates that the limits of technology likely extend far beyond our current boundaries. Across these vast dimensions of time and space, the rotation of the Milky Way assumes a foundational significance. It is far more than a natural mechanical process. It is the vital environment that permitted civilization to emerge. Rotation maintains structural stability. Stability fosters stars. Stars forge the necessary elements. Elements construct habitable planets. And planets host the evolution of consciousness. The slow, orderly revolution of the Milky Way across billions of years is the primary mechanism that provided the necessary conditions for conscious observers to develop on Earth. The Milky Way is destined to follow a similar trajectory, though this outcome resides on a timeline so distant that our Sun will have completed its life cycle long before the transition occurs. If a technological civilization is to persist across billions of years, it must eventually develop interstellar capabilities. The Sun's luminosity increases gradually over time, and long before it expands into a red giant, the environmental baseline of Earth will deteriorate. In approximately 1 billion years, elevated solar radiation will drive the evaporation of the oceans and dismantle the planetary climate system, rendering the surface uninhabitable for complex biology. Long-term survival on a cosmic timescale necessitates a departure from our home world. Theoretical discussions regarding the eventual expansion of a civilization across the galaxy are grounded in mathematical feasibility. Given sufficient time, even spacecraft traveling at a small fraction of the speed of light can systematically disperse throughout the galactic framework over tens of millions of years. Executing such an expansion involves profound logistical and technical challenges. Managing resources, navigating interstellar distances, mitigating radiation risks, and maintaining stable social or technical structures across generations. Yet the vast horizons of cosmic time provide the scope required for challenging objectives to gradually become technically viable. A highly advanced society might forego conventional physical spacecraft altogether, utilizing prolonged hibernation, digitized consciousness, or autonomous technological systems. It is even theoretically plausible that a sufficiently progressed civilization could manipulate stellar mechanics directly. Given an expansive timeline, the entire galaxy deforms like a fluid system. Our Sun carries the solar system through this landscape at a velocity of 220 kilometers per second, revolving around the galactic core while simultaneously bobbing up and down through the galactic plane. This vertical oscillation completes a full cycle roughly every tens of millions of years, bringing our system through the densest concentrations of the galactic disk. Certain theoretical frameworks evaluate whether these periodic crossings correlate with biological extinction events documented in Earth's geological history. As the solar system traverses the dense galactic equator, exposure to elevated stellar densities could alter gravitational boundaries, potentially destabilizing outer cometary reservoirs and increasing the frequency of inter-system impacts. While these correlations remain a subject of rigorous scientific analysis, they emphasize that the galaxy is not a passive background. It actively interacts with the long-term history of our planet. As time advances into the far future, the Milky Way will transition into a profoundly foreign state. The night sky will persist, but its features will bear no resemblance to our current view. The short-lived, high-mass blue giants will be the first to disappear, burning through their nuclear fuel rapidly like brief flashes across the cosmos. A duration of 40 million years appears vast from a human perspective, but within the context of stellar life cycles, it represents a rapid transition. Following the decline of these massive stars, the galaxy will dim, and the stellar landscape will be dominated by red dwarfs. These low-mass stars emit a modest luminosity, but possess lifespans capable of extending for trillions of years, far exceeding the current age of the universe. In that distant epoch, the final sources of illumination within the Milky Way will be these low-intensity stars, burning slowly, like fading embers in the cosmic dark. The galaxy will grow quiet, star formation will approach zero, supernovas will become exceptionally rare, and stellar nurseries will dissolve as the system completes its transition into senescence. Modern surveys have cataloged numerous systems that have already reached this mature phase, particularly the massive elliptical galaxies. These structures display a uniform reddish hue because they consist almost entirely of elderly stellar populations and lack the gas reservoirs required to initiate new star birth. Astronomers classify these systems as dormant or quiescent galaxies, indicating that their star-forming life cycles have reached a baseline conclusion. The Milky Way itself likely navigated an intensely turbulent infancy long before achieving its current spiral form. During its early phases, our galaxy was not characterized by an orderly spiral geometry. Instead, it regularly absorbed smaller dwarf systems, maintained elevated rates of star formation, experienced frequent supernova events, and featured a highly active central black hole. The system resembled a continuous storm, spanning billions of years before gradually settling into a state of structural equilibrium. The spiral arms organized, stellar trajectories stabilized into predictable orbits, and the galaxy eventually took the form we observe today. Yet, this stability represents a temporary phase, for transformation remains the enduring rule of the cosmos. The future evolution of the Milky Way involves inevitable shifts, and the upcoming merger with the Andromeda Galaxy marks merely an initial chapter. Billions of years from now, the reservoir of cold interstellar gas will gradually deplete, systematically lowering the rate of star formation until the galactic landscape begins to dim. Hot blue stars will grow increasingly rare, leaving the galaxy populated primarily by long-lived red dwarfs, shifting the night sky toward a subdued crimson spectrum as the system enters a long period of quiet decline. Many prominent stars in our current night sky will fade long before that era arrives. Betelgeuse, the distinct red supergiant in the constellation Orion, serves as a clear example. Its volume is immense. If positioned at the center of our solar system, its perimeter would extend past the orbit of Jupiter. Because of its massive proportions, its lifespan is exceptionally short, and it is expected to undergo a core collapse supernova within the next few 100,000 years, an imminent event on a cosmic timescale. When this collapse occurs, the explosion will generate enough luminosity to appear as a second sun in Earth's sky, remaining clearly visible during daylight hours for several weeks or months. Eventually, the energy will dissipate, Betelgeuse will vanish from view, and the outline of Orion will be permanently altered. Most of the constellations familiar to modern navigation represent temporary geometric arrangements. Because individual stars maintain independent trajectories through space, their positions shift continuously, though the vast distances separating them render this motion imperceptible across a human lifespan. Consequently, researchers are re-evaluating established models of galactic formation. It is possible that not all galaxies follow an identical evolutionary trajectory. Certain early systems may have undergone intense mergers during their initial formation, permanently disrupting the development of an organized disk. Alternatively, anomalies in the distribution of dark matter could account for this variance, since the dark matter halo dictates both the total mass and the structural stability of a galaxy. An atypical geometry within this halo would fundamentally reorient the rotation profile of the embedded stars. At present, these explanations remain theoretical postulations because astronomy limits us to observing final states rather than executing a direct playback of cosmic history. Unlike a laboratory experiment in chemistry, a researcher cannot reconstruct a galaxy under controlled variables to verify a hypothesis. Investigators must instead survey galaxies at diverse evolutionary stages, carefully assembling a chronological framework of cosmic development. This methodology operates much like archaeology, though the objective is uncovering the history of the universe rather than the remnants of a past society. The deployment of advanced space telescopes remains essential because they permit us to look directly into the past. Due to the finite velocity of light, Emissions from distant systems require vast timelines to span the gulf of space to our detectors. When instruments observe the absolute boundary of the observable universe, they are recording light that departed its source billions of years ago. The telescope functions effectively as a temporal vantage point, documenting the infancy of the cosmos rather than its current state. This data reveals the earliest generations of stars, the initial assembly of galaxies, and the dawn of cosmic structure, frequently challenging previously secure theoretical frameworks. Several early galaxies appear unexpectedly massive, display surprisingly mature disk geometries, and contain complex chemical compositions that should have required multiple generations of stellar life cycles to produce. These findings indicate that the early universe generated complex structures far more rapidly than established timelines calculated, suggesting that our current models omit key physical mechanisms or underestimate the velocity of early cosmic evolution. These older systems lack defined spiral patterns or a primary direction of motion, consisting instead of elderly stars drifting slowly through an unorganized structure. This state represents the mature phase of galactic evolution, where systems that once featured distinct rotation and prominent arms have lost their orderly mechanics through prolonged histories of mergers and interactions. In a broader sense, rotational velocity is the fundamental mechanism that prevents a galaxy from collapsing inward under its own gravitational weight. This principle governs structures across multiple cosmic scales. Planets rotate, stars turn, galaxies revolve, and event horizons spin. Angular momentum is a foundational rule embedded throughout the cosmos. When a cloud of interstellar material undergoes gravitational contraction, its rotational velocity naturally amplifies, a dynamic often compared to a figure skater pulling their arms inward to accelerate their spin. Numerous galaxies across the universe originated through this specific mechanism. Primordial gas clouds in the early universe collapsed under their own gravity, and even the faintest initial motion amplified systematically as the volume decreased, culminating in the slowly revolving structures observed today. This explains why a non-rotating galaxy generates significant interest within the scientific community. It indicates that a foundational evolutionary step deviated from expected outcomes, or the system experienced a major historical disruption. Historically, astronomers presumed that massive galaxies almost always display a clear directional rotation, varying only in velocity. However, deep space data from the James Webb Space Telescope has revealed unique early systems that appear exceptionally tranquil, lacking an organized rotational structure, and displaying randomized stellar trajectories similar to an unaligned cluster of stars. The anomaly rests on the extreme age of these systems, which date back to the early epochs of the cosmos. Standard theoretical models predict that early galaxies should be highly dynamic and turbulent, making the discovery of a low-rotation, massive early structure a significant analytical challenge. Evaluating the future trajectory of the Milky Way reveals that a reorientation of its rotational dynamics would initially alter our structural perspective, rather than immediately impacting individual stars. Our perception of cosmic stability depends significantly on the predictable regularity of the night sky. The sun rises along expected paths, constellations maintain their familiar configurations, and the Milky Way spans the heavens as a consistent marker. Across thousands of years, these elements have remained largely unchanged, encouraging the intuitive assumption that the cosmos serves as a permanent, static backdrop. However, if the internal mechanics of the galaxy deviate from equilibrium, the familiar geometry of the night sky will gradually grow unfamiliar. Certain stellar targets will exhibit shifts in brightness. Individual stars will drift from their recorded coordinates, and the established outlines of modern constellations will warp. The organized ribbon of the Milky Way will lose its structural symmetry, and the celestial landscape may feature expansive stellar clouds previously unseen from Earth. This transformation occurs because a disruption in orbital stability redefines the spatial order of the entire galaxy. Presently, the distribution of stars within our local neighborhood remains relatively uniform. Over long timelines, specific regions may experience high concentrations of stellar material, while other sectors are depleted, causing the night sky to lose its current structural equilibrium. Yet, this process unfolds with extreme slowness, spanning durations that outlast entire evolutionary epochs. A period of a few million years represents a minimal increment to a galaxy, but to biological life on Earth, it approaches an absolute horizon. Eventually, future observers may document a noticeable thickening of the galactic plane. The narrow, well-defined band of starlight will gradually broaden into a diffused expanse of light as stellar orbits drift away from a stable, disk-like geometry and migrate above and below the galactic equator. This expansion will systematically dismantle the spiral arms that characterize the Milky Way today. The galaxy will transition into a more randomized configuration, closely mirroring the architecture of massive elliptical galaxies documented in modern astronomical surveys. Certain neutron stars, known as pulsars, rotate hundreds of times per second, emitting highly focused beams of radiation that sweep across space like a lighthouse. When astronomers first recorded these remarkably precise signals, early discussions evaluated whether they represented artificial transmissions from an advanced civilization before confirming they were the natural outputs of rapidly spinning neutron star cores. The natural mechanisms of the cosmos routinely match the complexity of speculative concepts. The dynamics surrounding a black hole illustrate this perfectly. As an observer approaches an event horizon, the rate of time passage slows relative to a distant vantage point. This gravitational time dilation is a verified physical phenomenon detailed by Albert Einstein's general theory of relativity. Indeed, modern technologies like the Global Positioning System must actively calculate and correct for relativistic time discrepancies daily to ensure navigation remains accurate. The most profound mysteries of a black hole reside beyond its event horizon, where our current mathematical models of relativity encounter limits, and quantum mechanics cannot fully reconcile the extreme density. This boundary marks a current frontier in theoretical physics. Many researchers anticipate that a unified framework of quantum gravity will ultimately emerge from the study of these extreme regimes. The Milky Way operates as a colossal natural laboratory, executing physical processes involving extreme gravity, temperatures, and velocities that cannot be replicated within terrestrial facilities. Consequently, astronomy extends far beyond cataloging stars. It is an active investigation into the foundational properties of time, space, matter, and reality. The historical milestones of physics, from Johannes Kepler's orbital laws and Isaac Newton's gravity to Einstein's relativity and Edwin Hubble's expanding universe, all originated from observations of the night sky. Humanity consistently reinterprets its own baseline through the lens of the broader cosmos. The universe operates on timelines, where billions of years represent standard increments. Stellar life cycles mirror seasonal patterns, and the entirety of human history occupies a brief moment. Yet, it is precisely within this fleeting window, along the perimeter of an ordinary spiral arm, that a conscious species has successfully organized the tools to analyze, model, and comprehend the grand system it inhabits. For many, a clear illustration of the universe's dynamic nature occurs when observing a supernova. A massive star burns steadily for millions or billions of years before experiencing a rapid gravitational collapse, releasing more energy in a matter of seconds than our Sun will generate across its entire lifespan. Supernovas occur regularly across the Milky Way, averaging a few events per century, though interstellar dust and vast distances frequently obscure them from direct view on Earth. Nonetheless, human history contains precise empirical records of these events. In the year 1054, astronomers during China's Song dynasty documented a prominent guest star that was bright enough to remain visible in daylight for several weeks. Modern telescopes confirm that this event was a supernova explosion, and its expanding remnant persists today as the Crab Nebula. Supernovas are not merely spectacular astrophysical events. They are essential to the framework of biology. Crucial heavy elements, such as gold and uranium, are manufactured primarily within the extreme temperatures and pressures generated by these stellar collapses and neutron star mergers. The precious metals utilized in modern technology and human commerce were forged in the final moments of an ancient star's life cycle, distributed across the cosmos billions of years ago. Death is not an absolute conclusion within cosmic mechanics. The decline of a star yields entirely new structural forms. Depending on its initial mass, a star may transition into a white dwarf, a neutron star, or a black hole. Our Sun lacks the necessary mass concentration to form a black hole. Instead, it will expand into a red giant, roughly 5 billion years from now, altering the environments of the inner planets before casting off its outer layers to form a planetary nebula. The remaining core will persist as a dense, cooling white dwarf. Massive stars follow a far more intense trajectory, collapsing into neutron stars or event horizons. Neutron stars are exceptionally dense, compressing an entire solar mass into a sphere spanning only a few kilometers in diameter, where atomic structures are completely crushed under immense gravity, forcing electrons and protons to fuse into neutrons. The relationship between the broader cosmos and our local environment is deeply interconnected, shaping our climate, the formation of our moon, the availability of chemical elements, and the origin of life itself. The oxygen we breathe was manufactured billions of years ago through nuclear fusion inside a star that preceded our Sun. Humanity has never been separated from the mechanics of the universe. It is simply easy to overlook this connection amidst the infrastructure of modern life, where urban light pollution obscures the stars and high-density developments alter our view of the horizon. Observing the Milky Way from a truly dark location inspires a foundational realization. The scope of reality extends far beyond our daily boundaries. Prior to the development of empirical science, ancient cultures utilized narrative frameworks to interpret the pale ribbon of light spanning the night sky, viewing it as a celestial river, a path for deities, or a corridor for the transition of consciousness. This relationship shifted fundamentally when Galileo Galilei oriented a telescope toward the galaxy in 1610, documenting that the Milky Way was not a uniform mist, but a dense convergence of countless individual stars. This discovery marked the first time humanity mathematically confirmed that the night sky was vastly larger than traditional assumptions allowed. Subsequent efforts by William Herschel to map the galaxy's physical boundaries, followed by early 20th century observations, eventually demonstrated that the Milky Way was merely one system among an immense population of external galaxies. This conceptual transition reoriented our understanding of reality, confirming that neither our planet, our Sun, nor our host galaxy occupies a privileged, central position in the cosmos. Today, our modern surveys document trillions of independent galaxies, each hosting hundreds of billions of stars, which introduces the ongoing question: if the universe features such immense numbers of potential habitats, why does the interstellar medium remain silent? While a definitive solution to this inquiry has yet to be verified, the true milestone is that human civilization has developed the analytical capacity to rigorously pose the question. For instance, the core of the Milky Way remained obscured for decades due to immense concentrations of interstellar dust that absorb visible light. Infrared radiation can successfully penetrate these dust barriers, allowing modern instruments to resolve the galactic core with unprecedented clarity. The center of our galaxy is not a vacant void. Instead, it is an exceptionally crowded environment where stars reside in close proximity, gas clouds intertwine, and gravitational forces operate with immense complexity. Within that central regime, the stellar density is high enough that a night sky would remain illuminated, planetary orbits would face significant destabilization, and localized radiation fields would be intense. By comparison, our solar system sits in a tranquil, low-density region of the galaxy, a locational characteristic that likely provided the long-term environmental stability required for life to develop on Earth. This observation underpins ongoing research into the boundaries of the galactic habitable zone. Environments too close to the galactic core present significant hazards due to intense radiation and elevated supernova frequencies, while regions on the absolute periphery lack a sufficient abundance of the heavy elements required to form rocky planets. Our system resides within a balanced intermediate zone, demonstrating that habitability requires specific parameters at both a planetary and a galactic scale. While these models continue to evolve, they highlight that galactic architecture directly influences the long-term trajectory of biological life. Earth's history includes several periods of significant biological transition that some researchers correlate with our journey through the galaxy. As the solar system traverses the denser regions of the Milky Way's spiral arms, the statistical probability of encountering nearby supernovas or variations in cosmic radiation shifts, potentially impacting planetary climates or destabilizing outer cometary reservoirs. While these correlations remain a subject of active scientific debate, they remind us that our planet does not drift in absolute isolation. Every single orbit our solar system completes around the galactic center is a prolonged voyage through changing stellar neighborhoods and diverse interstellar environments. At times, our system may pass through massive molecular clouds spanning hundreds of light years. These cold, dense structures can alter the outer boundary conditions of the solar system, potentially influencing planetary atmospheres. In certain extreme cases, these interactions can even result in the central supermassive black hole being ejected from its home galaxy. When two supermassive black holes merge, an asymmetrical release of gravitational waves can generate a powerful directional recoil, launching the combined black hole directly out of the galactic center. This process leaves behind a galaxy devoid of a central black hole, a rare but mathematically sound outcome of modern orbital mechanics. Without that central concentration of mass, the orbital architecture of the remaining stars slowly adjusts, reorienting the long-term evolution of the entire system. The cosmos displays an immense variety of structural forms: ring galaxies with hollow centers, systems with elongated gravitational tails, structures displaying vast internal voids, and galaxies actively channeled by powerful astrophysical jets. When evaluated objectively, the universe presents an environment that is far more dynamic than Earth's deepest oceans, operating on a scale that humanity has only begun to survey. Furthermore, the Milky Way is far from silent. While the night sky appears motionless to the naked eye, observing the galaxy across non-visible wavelengths reveals a highly active landscape. Radio waves propagate through interstellar space. X-rays stream from the accretion disks of black holes. Supernova remnants accelerate high-energy particles, and neutron stars emit precise, repeating pulses like cosmic lighthouses. An immense volume of cosmic radiation continuously traverses the galaxy, passing through our immediate environment, completely undetected by human senses. Human biology is attuned to a remarkably narrow band of electromagnetic radiation. We perceive a limited spectrum of visible light, detect a specific frequency of sound, and cannot naturally observe magnetic fields, infrared light, ultraviolet rays, or X-rays. The true structural framework of the universe is far more complex than our raw senses imply. Consequently, modern telescopes do not function merely as magnifiers. They operate as specialized translators. The Hubble Space Telescope primarily observes visible and ultraviolet light. The James Webb Space Telescope surveys the infrared spectrum, and the Chandra Observatory records X-ray data. By synthesizing data across these diverse wavelengths, the scientific community gradually pieces together an accurate model of the galaxy. Despite these scenarios, astronomers do not anticipate an abrupt halt to galactic rotation, as such an event cannot occur through natural mechanisms. The primary focus of modern research is directed instead toward the slow, measured transformations already underway within the galaxy. For instance, a structural merger between the Milky Way and the Andromeda galaxy is practically certain. At present, Andromeda is approaching our galaxy at a velocity of roughly 110 kilometers per second. While this speed is significant, the vast distance separating the two systems means the initial interaction will not occur for approximately 4 billion years. When the merger begins, it will reshape the night sky into a spectacular astronomical display as Andromeda expands across the field of view. The two colossal systems will gradually pass through one another, reorienting stellar trajectories on a macro scale. Vast reservoirs of interstellar gas will undergo compression, triggering a massive wave of star formation that will brighten the entire galactic landscape. Yet, even during a merger of this magnitude, direct collisions between individual stars remain highly improbable because interstellar space is remarkably empty. The primary changes will occur within the gravitational orbits of the stars. Our solar system might be propelled toward the outer fringes of the newly forming system, drawn closer to the newly combined galactic core, or, in rare scenarios, ejected entirely into intergalactic space as a rogue system. If our world persists through that epoch, the night sky will bear no resemblance to the one we look upon today. Following the completion of the merger, the two spiral configurations will likely synthesize into a single, massive elliptical galaxy, which astronomers have designated Milky Way. This milestone will mark the conclusion of the Milky Way's current spiral era. Its distinct arms will dissolve, the familiar ribbon of starlight will vanish, and a more uniform stellar geometry will take its place. Reorganizations of this scale occur continuously across the broader universe. Many seemingly tranquil elliptical galaxies documented in our surveys are the products of historical mergers. Even today, the Milky Way continues to actively manufacture new stars. Within massive molecular clouds filled with hydrogen gas and dust, newly developing stars are continuously taking shape. Gravity causes localized regions within these clouds to slowly collapse inward, steadily increasing localized temperatures and pressures. Eventually, the core temperatures reach a threshold that ignites nuclear fusion, marking the birth of a new star. If a sufficient volume of material remains in the surrounding environment, a planetary system will organize alongside it. This process represents a continuous cycle within the universe. Stars form, mature, and decline, scattering elements that fuel the next generation of stellar systems. The long-term rotation of the Milky Way is the fundamental background dynamic that permits this cycle to persist. Rotation maintains the overall structural stability of the galaxy, drives the continuous motion of interstellar gas clouds and facilitates the ongoing exchange of material across different regions. If the Milky Way were to lose its rotational velocity, its overarching structure would begin to alter significantly. The system would initiate a slow collapse inward. Stellar orbits would lose their predictability, and concentrations of stars would migrate toward the galactic center, noticeably increasing the potential for stellar interactions. However, these structural changes would unfold over hundreds of millions of years. Biological life on Earth would likely pass long before the shifts became apparent, because human timelines are exceptionally brief compared to galactic dynamics. To a civilization, the evolution of a galaxy appears entirely static. Yet across cosmic time, it would represent a profound structural reorganization. As stellar trajectories shifted, the stability of our local solar system could be compromised. The frequency of neighboring stars passing near our system would likely increase, destabilizing the Oort cloud and sending an influx of comets into the inner solar system, which would raise the potential for planetary impacts. Furthermore, the solar system's broader orbital path through the galaxy could be permanently altered. There is a perspective regarding the Milky Way that is both deeply inspiring and grounded in physical reality. Humanity is not situated outside the galaxy, looking in. We are actively a part of the galaxy. Every single atom within our bodies originated inside ancient stars. When the universe first formed, it contained only the simplest chemical elements: hydrogen, helium, and a tiny trace of lithium. During that initial epoch, the cosmos lacked rocky surfaces, oceans, or biological structures. Indeed, the vast majority of the elements required to sustain life did not yet exist. Eventually, the first generation of stars emerged, initiating nuclear fusion within their cores and systematically forging heavier elements, including carbon, oxygen, silicon, and iron. These newly synthesized elements were subsequently dispersed into interstellar space upon the stars' deaths. Some were propelled by supernova explosions, while others drifted outward through gradual stellar winds. Through this ongoing process, the interstellar medium of the Milky Way was enriched over immense timelines. As concentrations of heavy elements increased, newly developed stars and planetary systems began to form. Ultimately, after billions of years, an ordinary yellow star emerged along the perimeter of one of the galaxy's spiral arms. Our Sun. Rocky planets coalesced around the Sun, and the third planet from the star maintained a temperate environment that permitted the persistence of liquid water. From these conditions, life emerged. Consequently, without the life cycle and eventual decline of early stars, humanity would not exist. The iron in our blood traces back to ancient supernovas. The calcium in our bones was once forged within stellar cores, and the phosphorus in our teeth was distributed by the explosions of ancient stars. Humanity is an unextraordinary outcome of long-term galactic evolution. This reality underpins the famous observation by many members of the scientific community: we are all made of star stuff. This is not a purely poetic sentiment. It is a literal chemical fact. Conversely, researchers also evaluate alternative cosmological outcomes. It is possible that cosmic expansion will eventually slow to a halt, initiating a reverse gravitational contraction. Under this model, galaxies would begin drawing closer together. Universal temperatures would steadily rise as matter compresses. Ultimately, the entirety of space-time would return to a state of extreme density, a scenario formalized as the Big Crunch. An alternative framework explores the possibility of dark energy continuously amplifying over time. In this scenario, the accelerating expansion would eventually overcome all structural forces, systematically dismantling galaxies, stars, planets, and eventually atomic bonds. This hypothesis is designated as the Big Rip. While these concepts resemble elements of speculative fiction, they represent legitimate mathematical outputs of modern cosmological models. At present, data remains insufficient to determine which trajectory is correct because our understanding of universal mechanics is still evolving. The anomalies of galactic rotation compose merely a small segment of a far more expansive puzzle. Yet, the presence of these unknowns is precisely what sustains our enduring fascination with the cosmos. If every dynamic were completely resolved, the night sky would lose its intellectual draw. The defining appeal of exploration rests not on the final answer, but on the certainty that further discoveries await. Perhaps a newly developed generation of space telescopes will observe an even earlier epoch of the universe. Maybe future surveys will document definitive evidence of an independent civilization. It is possible that dark matter will be explained by mechanisms entirely unrelated to new physical particles. Indeed, many frameworks held as foundational today may eventually undergo complete revision. The history of physics consistently follows this path of paradigm shifts. Isaac Newton's mechanics once appeared to offer a complete description of physical reality. Subsequently, Albert Einstein's relativity reoriented our understanding of space and time. Later, quantum mechanics transformed our concept of the microscopic world. Every major breakthrough redefines humanity's consensus reality. Consequently, our current model of the universe represents a milestone rather than a final destination. The Milky Way continues its slow, silent rotation, while the human endeavor to comprehend its mechanics continues to advance. Current cosmological models demonstrate that ordinary matter accounts for only a minimal fraction of reality. Stars, planets, interstellar gas, dust, and humanity itself compose this small percentage. All visible components of the cosmos combined represent less than 5% of the total universal mass energy budget. The remaining balance consists entirely of dark matter and dark energy. This indicates that our current scientific understanding addresses only the surface layer of reality. An insight of this scale reminds us that genuine science does not claim total knowledge. On the contrary, rigorous inquiry is built upon the active acknowledgement of the unknown. Maintaining this perspective is essential. A common childhood assumption treats scientists as the definitive custodians of universal answers. In practice, advanced research closely resembles navigating an uncharted, unilluminated landscape. Frequently, investigators must first determine if they are even formulating the correct questions. Consider the long-term trajectory of cosmic expansion. Will the universe expand indefinitely? A prominent school of thought suggests it will. Dark energy appears to continuously accelerate the expansion of space. If this trajectory persists across vast horizons of time, distant galaxies will drift further apart. Ultimately, every structure outside our local galactic group will recede beyond the observable horizon. Billions of years from now, a future civilization looking up at the sky would see no external galaxies whatsoever. They might logically deduce that the Milky Way is the entirely solitary system in existence, because light from external structures would no longer have the capacity to span the expanding distance. This concept provides a striking perspective on our era. It implies that humanity occupies a unique temporal window that permits a comprehensive view of the broader cosmos. An earlier epoch lacked the necessary structural maturity, while a later era will face the isolation imposed by dark energy. The present offers a temporary vantage point, where countless external galaxies remain entirely visible. Consequently, an increasing number of researchers suspect that conventional calculations underestimated the velocity of early cosmic structure formation. Alternatively, our current models may omit key physical mechanisms, This pattern frequently reorients the history of science. Whenever the research community believes it approaches a comprehensive solution, the universe introduces a newly documented anomaly. The cosmos essentially indicates that our current comprehension is merely a preliminary stage. The mystery surrounding galactic rotation follows this exact trajectory. Historically, scientists assumed that calculating the total visible mass of stars and gas within the Milky Way would accurately yield its rotation velocity. Yet empirical measurements revealed that stars residing on the galactic fringe travel at exceptionally high speeds. According to traditional Newtonian physics, these stars should have broken free from the galaxy's gravitational boundary long ago. However, they remained securely bound within the system. This discrepancy led to the postulation of dark matter. To this day, the true physical nature of dark matter remains unidentified. Yet, we can confirm that its gravitational presence sustains the entire structural integrity of the Milky Way. It is a profound realization that the overwhelming majority of mass within our host galaxy originates from a component that remains entirely invisible to conventional observation. Furthermore, the Earth is likely traversing a vast dark matter halo at this very moment, completely undetected by human senses. If future experimental physics successfully isolates a dark matter particle, it will stand as one of the most significant milestones in scientific history. Such a discovery would clarify not only local galactic dynamics, but also the macrostructure of the entire cosmos. Many astronomers share a distinct sentiment when reflecting on their work. Prolonged contemplation of the universe frequently inspires a profound sense of inner quiet. This state is neither excitement nor apprehension. Instead, it closely resembles the serene silence experienced after staring into the deep ocean. The cosmos does not offer immediate, definitive explanations. Instead, it presents an unfolding series of anomalies. Today, humanity successfully measures galactic rotation velocities, models major structural mergers, and images event horizon shadows. Simultaneously, a broader array of foundational questions continues to emerge. What is the literal nature of dark matter? Why is the expansion rate of space actively accelerating? What triggered the primordial quantum fluctuations at the dawn of time? Why does the arrow of time navigate strictly forward? How does conscious awareness arise from physical matter? Every single one of these inquiries possesses the depth to challenge entire generations of researchers. The Milky Way serves merely as the threshold to this domain. Stepping fully into the field reveals an architecture that is far more foreign than conventional assumptions imply. For example, historically established frameworks presume that galaxies formed along a standardized evolutionary trajectory. They emerged in a youthful state, initiated rotation, developed distinct spiral arms, achieved structural equilibrium, interacted with neighboring systems, and gradually matured. Following the deployment of the James Webb Space Telescope, multiple foundational aspects of this model began to shift. The data revealed that structural systems in the early universe achieved maturity far faster than standard timelines predicted. Several exceptionally ancient galaxies already exhibited significant mass concentrations. Some had already organized into regular, well-defined geometries. The available time within the early universe appeared insufficient to accommodate such development. According to previous theoretical models, these structures should not have attained such advanced stages so rapidly. Evaluating the architecture of the Milky Way naturally prompts an exploration into the potential developmental milestones of far future civilizations. If this conceptual exercise is extended across vast timelines, the scenarios lose familiarity. Consider, for example, a technological society that has progressed continuously for millions of years. Would its members retain any semblance of biological life? Perhaps they have fully integrated with non-biological intelligence. They might have dissociated entirely from planetary dependencies. It is even plausible that such entities would no longer prioritize interest in their home galaxy. For a sufficiently progressed society, concepts like stars, planets, and even physical bodies might simply represent localized milestones of their early evolution. Civilizations operating on this scale challenge the expressive capacity of modern human language. At times, researchers encounter the unique hypothesis that the universe may harbor widespread intelligent processes. Yet human sensory capabilities remain too rudimentary to detect them. Much like an ant lacking the cognitive framework to conceptualize the global internet, humanity might be blind to the structural markers left behind by highly evolved civilizations. While these scenarios remain theoretical postulations, the primary appeal of galactic research lies precisely in this dynamic. It consistently challenges our analytical community to evaluate phenomena entirely outside the scope of terrestrial experience. Time, space, civilization, and consciousness are all brought into question. We are left to wonder if other entities are actively evaluating the cosmos alongside us. In 1960, physicist Freeman Dyson proposed that a sufficiently progressed society might construct a vast network of structures around a host star to capture its total energy output. This concept is widely known as a Dyson sphere. In practice, this structure would likely manifest as a dense swarm of orbital solar harvesters rather than a solid shell. The core principle remains highly relevant. As a civilization matures, its energy demands increase, eventually requiring the direct utilization of its host star. Such an engineering feat would alter the star's light spectrum, prompting astronomers to actively look for stellar targets displaying anomalous behavior. The most famous example is Tabby's star. This stellar target exhibited irregular drops in brightness, leading to early speculation regarding the presence of an artificial structure. Subsequent data indicated that interstellar dust is the more likely explanation, yet the event remains a milestone. It marked the first time the scientific community rigorously evaluated whether a distant star might show signs of large-scale cosmic engineering. This reality shifts our focus from the direction of interstellar travel to the sheer magnitude of cosmic distance. Cinematic depictions of spacecraft traversing the galaxy in a matter of hours offer an idealized view, whereas the reality is completely different. Even if future propulsion methods achieve nuclear fusion or antimatter efficiency, the galactic scale remains remarkably vast. This has led scientists to consider whether truly advanced civilizations forego physical travel altogether. They might choose to digitize consciousness, deploy autonomous AI probes, or transition entirely away from biological forms. This explains why modern search methodologies have expanded beyond conventional radio signals. Astronomers now survey the skies for macro-engineering projects, anomalous infrared signatures, markers of stellar energy harvesting, or artificial orbital configurations. An advanced civilization might reshape an entire stellar system to sustain its energy requirements. Nevertheless, these discussions highlight a significant milestone. When humanity analyzes the galaxy, we inevitably begin to evaluate our own position within the cosmic hierarchy. The Milky Way is far more than a system of stars. It is the arena where civilization exists. Yet to this day, humanity has barely stepped beyond the perimeter of our immediate neighborhood. Our solar system occupies a remarkably small region of the galaxy. If the Milky Way were scaled down to the size of the North American continent, the solar system would be no larger than a small coin. The furthest distance reached by human engineering does not even approach the edge of that coin. Voyager 1, our most distant robotic probe, was launched in 1977. Traveling for nearly 50 years, it has only recently crossed the outer boundary of the solar system. The distance separating it from the nearest neighboring star remains profound. Therefore, some researchers offer a highly measured perspective regarding our solitude. The Milky Way may produce civilizations regularly, but the vast majority might possess brief lifespans. They emerge, signal their presence, and eventually recede. Separated by vast gulfs of time, their active eras rarely align, leaving the galaxy in a state of enduring silence. This represents one of the most sobering resolutions to the Fermi paradox. The universe is not devoid of activity. Rather, individual civilizations may struggle to sustain their technological eras over long periods. Conversely, alternative theories suggest a completely different explanation. Advanced societies might actively choose to remain unobserved. This concept is formalized as the dark forest hypothesis. The underlying premise suggests that cosmic resources are finite. Civilizations face inherent challenges in establishing mutual trust, and potential technological disparities can be immense. Under these conditions, the safest strategy is concealment. A society avoids broadcasting its location or initiating contact because the nature of the responding entity remains entirely unknown. While this perspective aligns with certain strategic models, it remains a philosophical framework lacking empirical support. Consequently, many researchers theorize that the universe may contain numerous planets hosting biology, while worlds that develop technological civilizations remain exceptionally rare. An additional challenge is the potential lifespan of a civilization. This factor is frequently overlooked, as we tend to assume that technological progress continues indefinitely. Yet historical data provides no such guarantee. The Roman Empire dissolved, the Maya civilization declined. The Bronze Age witnessed a widespread collapse, where multiple societies regressed almost simultaneously. Modern technology appears highly advanced, yet on a cosmic scale, our baseline security remains delicate. A global conflict, unmanaged climate shifts, or the misapplication of newly developed technologies could alter the trajectory of our species. Because life can exist in simple forms, bacteria, microbes, and single-celled organisms might be relatively common given a hospitable environment. Civilization introduces an entirely different set of variables. A civilization requires a prolonged window of environmental stability, complex biological evolution, the utilization of tools, language, memory, and the accumulation of technology. It is the outcome of multiple low-probability events aligning over vast spans of time. Our own planet illustrates this process perfectly. Life emerged on Earth roughly 4 billion years ago. Yet, for the vast majority of that history, the biosphere consisted solely of simple organisms. The proliferation of complex life occurred only within the last few 100 million years. As for human civilization, its recorded history spans less than 10,000 years. Our modern technological era accounts for a mere fraction of that time. If the history of the Earth were compressed into a single 24-hour day, the emergence of human civilization would occupy only the final seconds. The potential forms of life across the cosmos may be far more complex than those documented on Earth. Indeed, certain organisms might not depend on starlight whatsoever. Earth's deep-sea hydrothermal vents serve as a clear example, sustaining ecosystems completely independent of solar energy. This demonstrates that biological adaptability can exceed conventional assumptions. The unilluminated corridors of the Milky Way may not be as sterile as once believed. Deep beneath the icy crust of a distant moon, under the oceans of a rogue planet drifting through interstellar space, or even within environments built upon entirely different chemical foundations, life may already exist. We simply lack the technical capacity to detect it. As humanity entered the active search for extraterrestrial biology, scientists arrived at an important conclusion. The primary challenge in our celestial surveys may not be locating life itself. The true obstacle is finding civilization. This realization highlights a foundational truth. Human exploration of the cosmos is still in its infancy. Many elements of the universe have only entered our understanding within the last few decades. Take, for instance, exoplanets. Modern audiences are entirely accustomed to news regarding the discovery of newly identified worlds. Yet prior to the 1990s, humanity had not confirmed a single planet existing outside our solar system. During that era, researchers could only hypothesize that other stars might harbor planetary systems. Today, scientists have verified thousands of exoplanets. Some of these worlds reside directly within their star's habitable zone. Certain systems feature dual suns. Others are covered entirely by oceans. A few closely match the Earth in physical size. These findings continuously reshape our understanding of biology. This signified that humanity had truly listened to the universe for the first time. Historically, astronomy relied almost entirely on light. Telescopes were essentially a way of seeing. With the advent of gravitational waves, humanity began to hear. In the future, scientists hope to utilize gravitational waves to study the earliest epochs of the universe, because there are certain extreme regions from which light can never escape. Because 100 years earlier, Einstein predicted that when massive objects accelerate through space, they disrupt the fabric of space-time, generating gravitational ripples. Many at the time believed that these waves would be far too faint to ever be detected by instruments. Yet, the LIGO experiment achieved exactly that. Two black holes collided over 1 billion years ago. The resulting ripples in space-time traveled across the cosmos and were ultimately captured by detectors on Earth. Even the supermassive black hole at the galactic center may have undergone multiple mergers. Scientists theorize that whenever galaxies collide, their central black holes will eventually draw near one another. They will orbit each other, releasing gravitational waves before finally combining into an even larger black hole. In 2015, humanity directly detected gravitational waves for the very first time. The significance of this discovery is immense. Some studies even suggest that a portion of the stellar cluster surrounding our own sun may have originated from a smaller galaxy absorbed by the Milky Way long ago. In other words, humanity may have emerged in the wake of an ancient galactic collision. This is a profound realization because it means the Milky Way is not a system that simply grew up in isolation. It is closer to a colossal structure pieced together from countless historical remnants. In a way, the reason the Milky Way grew to its current immense scale is precisely because it has been continuously gathering material. This is a fundamental concept in modern cosmology. Massive galaxies rarely form all at once. They are the cumulative result of continuous mergers, interactions, and assimilation. Within the interior of the Milky Way, many traces of this dynamic history are preserved. In a way, the reason the Milky Way grew to its current immense scale is precisely because it has been continuously gathering material. This is a fundamental concept in modern cosmology. Massive galaxies rarely form all at once. They are the cumulative result of continuous mergers, interactions, and assimilation. Within the interior of the Milky Way, many traces of this dynamic history are preserved, ultimately leaving them drifting around the galaxy like frayed ribbons. One of the most notable examples is called the Sagittarius Dwarf Elliptical Galaxy. It is currently being absorbed by the Milky Way. The entire process is exceptionally slow, unfolding over billions of years. But eventually, that small galaxy will disappear completely, and its stars will become part of the Milky Way. By comparison, The Milky Way today is closer to an ocean that has settled into a stable phase, calm on the surface. Yet underneath, deep currents still flow. For example, the outer fringes of the Milky Way continue to pull in small dwarf galaxies to this day. Scientists have discovered numerous disassembled stellar streams surrounding the galaxy. These stars originally belonged to smaller separate galaxies. As they drew near the Milky Way, tidal gravity systematically pulled them apart. The Milky Way today is actually far more tranquil than it was during its youth. Galaxies in the early universe were routinely much more chaotic. Stars formed at a much faster pace, collisions were more frequent, and black hole activity was far more intense. Many young galaxies even ejected energetic streams of particles that pierced through the entire system. The energy of those astrophysical jets was sufficient to influence regions spanning hundreds of thousands of light years. The Milky Way is exactly the same. If a distant civilization were observing Earth right now, what they see might be the age of the dinosaurs, or perhaps even earlier. Distance in the universe translates directly into time, which is precisely why many astronomers observe that the cosmos is never a static image. It is closer to a history unfolding and propagating through space. The rotation of the galaxy is similarly a chapter within this history, because a truly synchronized now does not exist in the universe. The present of the Sun is 8 minutes behind the Earth. The present of the galactic center is 26,000 years behind the Earth, and the present of Andromeda is delayed by 2.5 million years, which means when you look toward the Andromeda galaxy tonight, what you are actually seeing is Andromeda as it existed 2.5 million years ago. At that time, our human ancestors had not even emerged on Earth. The night sky you look upon at this moment is actually a blend of different eras of the cosmos. The light from some stars began its journey decades ago. Some began thousands of years ago. Much of the light from the deep galaxy departed its source when Earth was still home to ancient civilizations. In a sense, every time humanity gazes at the stars, we are actively looking into the past. This realization fundamentally alters our understanding of the present. It inspires a very unique realization. You suddenly understand that you do not live beneath the sky, but rather you live inside the universe. The stars above your head are not mere points of light fixed upon a canopy. They are real, physical suns. Some of them are dozens of times larger than our own sun, while others have already ceased to exist. It is just that their light has not yet finished the final leg of its journey. If the speed of light were a train that never stops, traveling from one end of the galaxy to the other, it would still require 100,000 years. This scale has already stretched far beyond human intuition. So frequently, humanity does not truly conceptualize what the word galaxy implies. We have simply grown accustomed to its presence. Those who see the Milky Way for the first time in childhood usually share the exact same feeling: awe, particularly in places far removed from city lights. The summer night, Milky Way appears remarkably distinct, like a glowing river arching across the heavens. Not because it is loud or bustling like a city. Quite the contrary. The galaxy is quiet, approaching absolute stillness. Where the true similarity lies is in the structure. The galactic center is like the oldest, most densely populated district. The outer spiral arms are like new sectors continuously expanding outward. In some areas, stars are densely packed, while other regions are sparse and remote. Some stars are newly born, while others are nearing the end of their lifespans. The entire city spans 100,000 light years, and the Milky Way serves as the vessel for this vast expanse of time. It preserves ancient stars. It preserves black holes. It preserves the cycling of elements. And it preserves the history of the cosmos itself. At times, astronomers compare the Milky Way to a grand metropolis. And what is most remarkable is that many of these stars formed during the earliest phases of galactic history, meaning when they were born, the Milky Way likely did not yet possess the spiral arms it has today, and the Earth did not exist at all. If an ancient civilization were to reside within one of these clusters, their recorded view of galactic history would stretch far longer than our own. Granted, there is currently no evidence to suggest life exists there, but the mere concept is deeply profound, because it reminds us that there are structures in the universe incredibly more ancient than the entirety of human history. And the truly ancient components of the Milky Way are the globular clusters. They represent some of the oldest structures within the galaxy. Many globular clusters possess ages exceeding 12 billion years, making them far more ancient than our Sun. These clusters are primarily distributed throughout the sparse outer halo of the galaxy, holding hundreds of thousands of stars tightly bound together. They drift around the Milky Way like ancient monuments. And this disparity in scale easily distorts our perception of time. For example, the extinction of the dinosaurs seems impossibly distant from a human perspective. Yet relative to the age of the Milky Way, that event occurred less than a single galactic orbital period ago. In the time it takes the solar system to orbit the galaxy once, the entire age of the dinosaurs has only passed by half. In other words, since the decline of the dinosaurs, the solar system has not even completed one full journey around the center of the Milky Way. This sense of scale fundamentally alters our understanding of what is ancient. For instance, the famous North Star, Polaris, will not remain the pole star forever, because the Earth's rotational axis undergoes a slow precession, and the stars themselves are continuously moving. Tens of thousands of years from now, the constellations in our night sky will shift their patterns. Orion will warp, the Big Dipper will disperse, the Milky Way will remain, but the familiar tapestry of stars will have transformed. Many of us assume in childhood that the constellations are permanent and unchanging, but in truth, that is merely because human lifespans are so brief. A single instant on a cosmic scale appears to us as an eternity, and this slow transformation inspires a very profound realization. The Milky Way appears eternal, yet in reality, it is in a state of constant flow, much like a river. The galaxy you look upon tonight and the galaxy from hundreds of millions of years ago are not identical. Even the specific arrangement of stars composing our local night sky will slowly alter in the future. In a sense, humanity's ability to clearly observe the structure of the Milky Way is itself a stroke of locational fortune. And remarkably, the spiral arms themselves slowly shift over time. The solar system will not remain near the exact same arm structure indefinitely. Hundreds of millions of years from now, our galactic sky may look entirely different. In fact, the galactic night sky during the age of the dinosaurs was already subtly distinct from the one we see today. It is just that the change unfolds so gradually that it eludes direct human perception. If the solar system were located near the chaotic galactic core or inside a major star-forming region, the environment for Earth would likely be far more hazardous, because in those areas, supernovas are more frequent and radiation is more intense. Indeed, the night sky itself would look entirely different. In fact, if you stood near the center of the Milky Way, the night sky would be astonishingly bright. The heavens would be densely packed with stars, to the point where true darkness would never fall. The reason our night sky on Earth today remains relatively dark is simply because the solar system sits out toward the galactic fringes. Where stellar density is low, certain zones maintain a higher density of matter. Interstellar gas is more easily compressed there, triggering the formation of numerous new stars, which is precisely why, within the galactic arms, we always observe an abundance of bright, blue young stars, because those regions serve as stellar nurseries. As for our solar system, we happen to reside along a relatively minor branch of a spiral arm, known as the Orion Arm. It is situated between two much larger spiral arms, making it a relatively peaceful neighborhood within the galaxy. Many people assume that spiral arms are fixed physical structures, but in reality, they are closer to a cosmic traffic jam. It sounds like a strange comparison, but astronomers have discovered that the spiral arms are not permanent clusters of specific stars. Many stars will enter a spiral arm and subsequently leave it behind. A spiral arm is more precisely understood as a density wave, much like a localized traffic bottleneck on a highway. The individual cars are continuously moving through, yet the region of high density remains in place over time. The spiral arms of the Milky Way are a similar phenomenon. The stars within the galaxy each follow their own distinct orbital paths. The regions closer to the galactic core revolve much faster, while the outer regions are comparatively slower. This structural phenomenon is known as differential rotation, and differential rotation is one of the primary reasons the Milky Way is able to form its distinct spiral arms. So frequently, we mistake the universe for a static place. But in reality, the cosmos is more dynamic than any ocean, except it measures its waves in millions of years, and its tides in hundreds of millions of years. Furthermore, the rotation of the Milky Way does not occur at the same speed across all regions. This detail is fundamentally important because the galaxy does not spin like a vinyl record. A vinyl record exhibits rigid body rotation, where the further out you go, the faster the linear speed becomes. But that is not how the Milky Way operates. In truth, if you were to take the movements of the Milky Way and play them back in fast forward, it would be a breathtaking sight. The spiral arms would flow slowly, like whirlpools in a vast ocean. Stars would migrate across the galactic disk. Nebulae would continuously stretch, dissolve, and recombine. New stars would ignite. Old stars would fade. Supernovas would erupt in the darkness, and the central black hole would occasionally consume matter passing nearby. Dwarf galaxies would approach from the fringes, before being slowly disassembled by the Milky Way's gravitational tides. The entire galaxy has always been in a state of constant transformation. It is just that the shifts are exceptionally slow, far too slow for a human lifespan to directly perceive. At this very moment, our entire solar system is still traveling around the galactic center at a speed of 220 kilometers per second. Yet we cannot perceive it, because the Milky Way is simply too vast. So vast that even at this astonishing speed, it still requires over 200 million years to complete just a single orbit. And even as you listen to these words right now, the Milky Way continues to rotate, quietly, slowly, traversing the long horizons of cosmic time. From the moment ancient humans first looked up at the Milky Way, this curiosity was already present. The people of that era did not know what stars were. They did not know what the Milky Way represented. And they certainly had no concept of black holes, dark matter, or galactic collisions. Yet they still looked up at the sky in the dark of night, because the Milky Way always inspires a distinct feeling, as if something profound is hidden out there. And today, thousands of years later, humanity has finally begun to slowly comprehend that the pale band of light is actually a colossal rotating galaxy, holding hundreds of billions of stars within its frame. And we are living right upon one of its spiral arms. And beyond the Milky Way lie trillions of other galaxies. Thus, the universe, in a sense, is a reality where one can never truly arrive at a final destination. The more you understand it, the more unknowns you uncover. Yet it is precisely for this reason that humanity continuously looks upward, continuously building larger telescopes, continuously launching new space probes, because curiosity is an intrinsic part of civilization itself. How the universe began, how structure forms, how order is maintained, why life emerged, and whether all of this will eventually reach a conclusion. And perhaps that is where the true fascination lies, because humanity will never be able to fully survey the entire universe. The Milky Way alone is already so immense that it challenges exploration. Even if an interstellar civilization were to emerge in the future, it might require millions of years just to navigate across our own galaxy. And the Milky Way happens to be one of the most direct stages for these mysteries. It was precisely due to the anomalous galactic rotation curve that humanity realized dark matter must exist. The influence of black holes on stellar orbits allows us to investigate gravity under extreme regimes. And the puzzle of galactic formation connects directly to the early evolution of the cosmos. Therefore, when we discuss the concept of a galaxy's rotation altering over time, we are not merely talking about a single system of stars. We are using the Milky Way to reach out and touch much grander inquiries. Modern physics exists in a remarkably subtle state. On one hand, it is exceptionally successful, capable of predicting black holes, calculating stellar evolution, and enabling humanity to land on the moon. On the other hand, it is visibly incomplete because we have yet to uncover the true nature of the most significant components of the universe: dark matter, dark energy, quantum gravity, and consciousness. These questions remain as silent as deep space. In truth, humanity's current understanding of the Milky Way is only the beginning. For example, what dark matter consists of remains unknown. What dark energy represents is also unknown. Why cosmic expansion is accelerating lacks a definitive answer. Indeed, even ordinary matter is something we have yet to fully comprehend. In a way, the Milky Way is not just rotating, it is generating observers. And perhaps elsewhere in the cosmos, similar journeys are unfolding. Maybe on some distant world, an entirely different form of life is also lying in the dark, looking up at their own galaxy. They might be asking the exact same questions. Why do galaxies rotate? Why does the universe exist? What lies beyond the event horizon? And perhaps they share the same quiet realization that one day, the familiar night sky will transform. Because within the known cosmos, life on Earth has managed to study black holes, comprehend galaxies, measure the age of the universe, and model the future of the Milky Way. This achievement is extraordinary, especially when you contemplate that the atoms composing your body right now originated deep within the cores of ancient stars, and those very atoms are now analyzing the cosmos. It is a beautiful loop. The universe manufactures elements through the stars. The elements compose life, and life turns back to comprehend the universe. The universe does not register human success or failure. It simply exists. Stars continue to burn. The galaxy continues to rotate, just as it did billions of years ago. and as it will billions of years from now, while human history remains a beautiful, brief moment in the dark. Naturally, this sense of cosmic scale does not mean humanity lacks purpose. Quite the contrary. It is precisely because the universe is so vast that consciousness becomes precious. Yet remarkably, it is precisely this small scale that brings a sense of quiet clarity to many. Because when you truly conceptualize the cosmic scale, many daily anxieties suddenly appear far less significant, which is why so many prefer to look up at the stars late at night. The Milky Way inspires a realization that we are merely brief travelers in the cosmos, and this perspective is not pessimistic. Rather, it is profoundly peaceful. It was an image of Earth taken by Voyager 1 as it was leaving the solar system, looking back across space. In that photograph, the Earth is a single pixel suspended in a beam of sunlight, almost invisible. Yet Sagan remarked that every conflict, every empire, every joy, and every civilization in human history occurred upon that tiny dot, and the Milky Way amplifies this perspective even further, because the entirety of human civilization, when placed within the galaxy, is as small as a grain of dust. That realization would fundamentally redefine our concept of home. For thousands of years, the sun has been the center of our sky, dictating day and night, the seasons, and life itself. Yet, on a galactic scale, the sun is merely one of hundreds of billions of stars, and the Earth is even more minuscule. The legendary astronomer Carl Sagan famously noted that reality when speaking of that iconic photograph, the pale blue dot. Perhaps many years from now, when humanity truly leaves the solar system and ventures deep into the galaxy, we will understand for the first time just how immense the Milky Way truly is. Because today, we remain anchored to a terrestrial perspective. The Milky Way we see is merely a ribbon of white light across the sky. But if one day you were to journey beyond the solar system, traveling toward the outer limits of the galaxy, you would slowly realize the sun is just an ordinary star among hundreds of billions. New stellar systems will continuously appear, new nebulae, new structures in deep space, while the sun grows steadily dimmer. Ultimately, it will fade into the galactic backdrop, an indistinguishable point of light. And if it hosts a planetary system, any life upon those worlds will witness the galaxy drifting further and further away, until eventually the night sky is reduced to absolute darkness. This scale of isolation stretches beyond the bounds of ordinary human experience. Yet it is precisely this quality that makes the Milky Way so captivating, because it is not merely a collection of stars. It is closer to an epic narrative of time, motion, birth, and decline. And humanity happens to exist at a specific moment in the story, to look up and observe it. Furthermore, there are stars that are actively escaping the galaxy at high velocities. Scientists have identified a class of hypervelocity stars. Their speeds are sufficient to break free from the galaxy's gravitational pull, some traveling at over 1,000 kilometers per second. It is currently understood that these stars likely originate from the galactic center. When a binary star system passes close to the black hole, one star is captured by its gravity, while the other is launched outward, functioning like a cosmic trebuchet. And so, a star begins its solitary journey into intergalactic space. Billions of years from now, it will leave the Milky Way behind forever. In truth, many regions of the Milky Way are far less static than they appear on the surface. For instance, within the galactic disk, there exists a vast population of invisible rogue planets. These planets are not bound to any host star, drifting alone through the darkness of the galaxy. They may have once belonged to a stellar system before being gravitationally ejected, destined to wander indefinitely. If you stood upon the surface of such a world, the sky would be entirely dark. No sun, no day or night, only the incredibly faint starlight of distant systems. In a sense, that is the true definition of deep space. And within the Milky Way, billions of such worlds may exist, perhaps even outnumbering the stars themselves. And remarkably, humanity has discovered in recent years that the central black hole was likely far more active in the past than it is now. Evidence suggests that millions of years ago, a massive eruptive event occurred, creating two colossal high-energy structures extending above and below the galactic plane, known as Fermi bubbles. These two immense structures look like bubbles of light extending from the galactic core, spanning tens of thousands of light years. Scientists believe they likely originated from a period of intense activity at the center of the galaxy, meaning the galactic center, which appears entirely serene today, may have been highly dynamic in the past and in the future. It could potentially awaken once more. Consequently, today, more and more researchers are concluding that a galaxy and its central black hole likely co-evolve. They do not exist independently. Instead, they actively shape one another. The reason the Milky Way takes its current form today may be closely linked to the long-term history of the central black hole's activity. And what is even more extraordinary is that the central black hole is not merely a passive consumption mechanism. It may actively influence the evolution of the entire galaxy. The central black holes of many galaxies eject colossal streams of high-energy particles. These astrophysical jets can reach lengths of hundreds of thousands of light years. They heat the surrounding interstellar gas, suppressing the formation of new stars. In a way, the black hole acts as a regulator for the galaxy. Some stars can even complete a full orbit around the galactic core in just over a decade. And based on orbital calculations, there must exist an object at that location of immense mass and remarkably small volume. Ultimately, all empirical evidence pointed to a supermassive black hole. This was actually the first time humanity indirectly observed the black hole at the center of our galaxy, not through a photograph, but rather through stellar motion. In a sense, it was through the rotation of the Milky Way that we uncovered the existence of the black hole. In fact, near the center of the galaxy, stars travel at astonishing velocities. Scientists have long tracked the orbits of these specific stars, discovering that they revolve at high speeds around an invisible concentration of immense mass. Albert Einstein famously demonstrated that gravity is not a conventional force, but rather the curvature of space and time. Mass curves the fabric of space-time, and planets and stars simply follow the paths generated by that curvature. You can visualize a taut sheet of rubber. If you place a heavy bowling ball upon it, the surface indents. When smaller objects pass by, their trajectories are altered. The Milky Way operates on a similar structural principle, except on a scale that challenges the imagination. And the supermassive black hole at the galactic center represents one of the deepest depressions in the entire fabric of space and time. So frequently, when we discuss the Milky Way, we subconsciously imagine a tightly packed structure. But in reality, it is closer to a gravitational ecosystem spanning 100,000 light years. And within this system, gravity dictates everything. Stars revolve around the galactic core. Gas clouds collapse under gravitational weight. Black holes alter nearby orbits. Dwarf galaxies are disassembled by galactic tides, and even light bends when passing near immense mass. What truly fills the universe is not matter, but rather distance. And this immense sense of emptiness is one of the hardest concepts for human intuition to grasp. For instance, light traveling from the sun to the earth requires 8 minutes. It sounds brief, but the speed of light is 300,000 kilometers per second, meaning even at the absolute speed limit of the universe, it takes 8 minutes to span that distance. And the nearest star system resides roughly 4.2 light-years from the sun. If we dispatched the fastest modern spacecraft today, the journey would require tens of thousands of years. The galactic scale is even more exaggerated. And stranger still, the stars within the galaxy almost never actually collide. This contradicts basic human intuition, because when looking at photographs of the Milky Way, the stellar environment appears incredibly crowded. But that is merely because the galaxy is vast. If you were to shrink the sun to the size of a single grain of sand, the nearest neighboring star would be hundreds of kilometers away. Therefore, the true state of the Milky Way is closer to a grand, sparse mist of stars, where the vast majority of space is entirely empty. If you truly contemplate the rotation of the Milky Way, you realize that this phenomenon is profoundly extraordinary. Because the galaxy is not a solid object, it is not a massive disk of metal, there is nothing physical linking the stars together. The distances between stars are so vast that they approach absolute emptiness. Yet even so, the entire Milky Way maintains a macro-scale order. Hundreds of billions of stars, like a celestial tide, revolve together around the galactic center. This image, in itself, approaches a cosmic miracle, and the Milky Way functions like a grand river of time, arching across the night sky. It witnessed the Earth during the age of dinosaurs. It witnessed the birth of the very first stars, and in the future, it will witness the decline of the sun, the merger of galaxies, the transformation of galactic structures, and eventually, the passing of human civilization. But at least for this moment, it continues to rotate, slowly, quietly, like a cosmic whirlpool spanning over 10 billion years, and we are living within its spiral arms.